Why does the universe glow with ancient light? How did early light become today's microwave background? What noise puzzled Penzias and Wilson in 1964? There is a quiet hum that fills the cosmos, a faint glow that you cannot see with your eyes. It is all around us, day and night, in every direction we look. This mysterious light is invisible to human sight, yet it bathes the entire universe in a gentle, uniform warmth. It's as if the early universe itself left behind a soft whisper, an afterglow from a time long, long ago. In the darkness of space, beyond the twinkling stars, this ancient radiance endures, carrying secrets from the dawn of time. Long before there were stars or galaxies, before the earth or sun had formed, the universe was a very different place. It was a young, hot ocean of energy and particles, a glowing fog filling all of space. Imagine that newborn cosmos, only a few 100,000 years old, suffused with brilliant light. In those earliest days, the universe was so dense and fiery that light could not travel freely. It was trapped, scattered endlessly by free electrons in a thick cosmic haze. Space itself glowed like the inside of a star, bright and blinding, with no dark corners anywhere. But as the universe expanded and cooled over time, a remarkable transformation occurred. At around 380,000 years after the Big Bang, the temperature finally fell enough for electrons to settle down and bind to nuclei, forming the first simple atoms. This might sound unremarkable, but it changed everything. The fog of charged particles cleared as electrons found homes orbiting hydrogen and helium nuclei. The cosmos went from opaque to transparent, almost in an instant on cosmic timescales. And when the universe suddenly became transparent, the light that had been trapped was finally free. In that moment, the brilliant glow that filled the young universe was released to travel unimpeded through space. One could imagine that if some observer had been present at that epoch, impossible as it was for life to exist then, they might have witnessed the entire sky blaze bright as the fog lifted, a flash of light that would gradually dim and redden over the eons. What had once been a seething, blinding brightness could now stream across the cosmos. Those first rays of free light have been journeying for nearly 13.5 billion years, ever since that early era of transparency. As they travelled, the universe continued to expand, stretching the fabric of space, and stretching the light itself into longer and longer wavelengths. Over billions of years, that brilliant flash of light was redshifted beyond the visible spectrum, sliding through infrared colours and eventually into the microwave range that it lies in today. Over the eons, the radiation that was once as hot and energetic as the surface of a star has grown faint and cold. Today, that ancient light has cooled to a mere whisper of its former self. What was once a searing brilliance now registers as a cold, faint glow, only a few degrees above absolute zero. Scientists measure its temperature at about 2.7 degrees on the Kelvin scale, just a couple of degrees above the coldest temperature anything can possibly reach. Absolute zero, by definition, is about 273 degrees Celsius, or 459 degrees Fahrenheit, the point at which all thermal motion ceases. So 2.7 Kelvin, roughly 270 degrees, is extraordinarily cold. This means the entire universe, even the emptiest reaches of space far from any star, is gently warmed to about 2.7 K by this all-pervasive glow. At this frigid temperature, the light is no longer visible to our eyes. It has been shifted far out of the visible range by the expansion of the universe into the realm of microwaves. What was once bright, blue-white light has been stretched and redshifted into invisible microwave radiation. We can't see microwaves with our eyes, but they are very real. The same kind of waves that heat food in a microwave oven, only vastly weaker and coming from every patch of sky. This is the cosmic microwave background, often affectionately called the CMB, the afterglow of the Big Bang. It surrounds us, filling space like a faint memory of the universe's fiery birth. Wherever we point a sensitive radio or microwave antenna in the sky, we encounter this soft background glow. It's almost perfectly uniform, the same gentle whisper in all directions, with only the tiniest variations in intensity. Think of it as a kind of cosmic wallpaper, or perhaps a subtle perfume that permeates the entire room of the universe, always present, but so faint and unchanging that it's easy to overlook. For a long time, no one knew this glow was there. It's completely invisible, without special instruments, and it doesn't announce itself loudly. Humanity went about its history, oblivious to this silent cosmic presence. Yet it was there nonetheless, the universe's way of preserving a memory of its own birth, hidden in plain sight. Imagine standing outside on a clear night, feeling the cool air on your skin. You gaze up at the stars. Perhaps you can see the Milky Way as a delicate band across the sky. All seems quiet and dark between those stars. But unbeknownst to your eyes, the space around you is aglow with microwaves from that primeval fireball. If our eyes were tuned to those wavelengths, the night sky would never be truly dark. It would everywhere glow with a soft, invisible light. We live our lives immersed in the afterglow of creation without ever perceiving it directly. The idea that such an afterglow might exist was hinted at by scientists well before it was actually found. In the mid-20th century, a few forward-thinking researchers pondered the consequences of a hot Big Bang origin of the cosmos. If the universe began in a hot, dense state, they reasoned, then as it expanded and cooled, the leftover radiation from that fiery beginning should still be around, just stretched out and cooled down. In the late 1940s, physicists predicted that the universe should be filled with a relic radiation, perhaps just a handful of degrees above absolute zero, essentially a faint heat left over from the Big Bang's initial blaze. However, at that time, these predictions were not widely known or taken very seriously by the broader scientific community. The idea was intriguing, but easy to dismiss. After all, how could one possibly detect a feeble whisper of heat filling all of space? Technology then was not as advanced, and cosmology itself was still maturing as a science. In those days, the very origin of the universe was a subject of debate. Not everyone agreed there even was a Big Bang. Some believed instead in a steady-state universe with no beginning, which would not have such a leftover background radiation at all. So the notion of the cosmic afterglow lingered in the background of theoretical discussions, waiting quietly for someone to listen to the sky in just the right way. Through the first half of the 20th century, the universe kept this oldest light hidden from our view. No one had the instruments to see it, and few had the insight to search for it. It's humbling to realize that even as we invented radio antennas and began tuning into the cosmos, this vast background song of the universe was playing continuously, unnoticed. Every time someone turned an old-fashioned television set between channels and saw static, a small part of that snow on the screen was actually caused by this ancient light. Without knowing it, people had been catching tiny glimpses of the Big Bang's echo in the static on their TV screens and the faint hiss between radio stations. but it was mixed with so much other noise that its true nature remained hidden. In essence, the cosmic microwave background is like the fading glow of embers after a great cosmic fire. Picture a campfire after the flames have died down. Even when the fire is out, you still see a dim orange glimmer in the ashes, glowing softly as it cools. The Big Bang was like an unimaginably immense fireball, and the CMB is its faint, long-lived ember, stretched and cooled over billions of years, but not completely extinguished. It carries within it a story. Encoded in its gentle glow are clues about the early universe's conditions, its composition, and how it would eventually give rise to galaxies and stars. But for a long time, this cosmic story remained unread. Some call the cosmic microwave background a baby picture of the universe, because, in a way, it shows the cosmos when it was a mere infant, just out of the opaque womb of its first moments. But before we could actually see that baby picture in detail, we had to realize it was there at all. For years, the universe's oldest light remained an invisible backdrop, its existence suspected by a prescient few, but empirically unseen. All of that was about to change in the mid-20th century. Quite by accident, under a calm sky, the universe was about to reveal this long hidden light to human eyes for the very first time. On a crisp, clear day in the spring of 1964, two young radio astronomers were hard at work in Holmdel, New Jersey, listening to the sky. The morning sunlight gleamed off the curved metal surface of their giant antenna as dew from the night still clung to the grass around it. The air was calm and quiet, nearly idyllic, and it seemed like a perfect day to listen to the whispers of the cosmos. They had at their disposal an unusual instrument, a large, horn-shaped antenna that looked like a giant metal megaphone pointed upward. This antenna, originally built to communicate with early satellites, had become a tool for peering into the invisible whispers of the cosmos. Its broad mouth gathered radio waves from the sky, funneling them down to sensitive detectors. Penzias and Wilson, the two scientists tending this great horn, were trying to measure radio emission from our galaxy and beyond. They expected to hear faint, natural static from the Milky Way, and perhaps other cosmic sources, but mostly quiet otherwise. Instead, they encountered a persistent hum that they could not explain. From every direction they pointed the antenna, the same mysterious noise appeared. It was a steady, low-level hiss, not loud, but insistent and unvarying. Day or night, sky or horizon, winter or summer, this background hum was always there. At first, Penzias and Wilson assumed something must be wrong. Perhaps there was interference from a nearby city, or human-made radio signals somehow contaminating their measurements. They double-checked every piece of their equipment. Could it be an electronics issue? A faulty component in the detector amplifying some internal noise? They calibrated and recalibrated. Yet the hum persisted. Puzzled, the pair began systematically ruling out possible culprits. They knew that radio noise can come from many sources: thunderstorms on Earth, the sun's activity, or even radiating gas in the Milky Way galaxy. But this sound was strangely uniform. It didn't seem to come from any one direction or source. It was everywhere they looked. If it were coming from a particular celestial object, pointing the horn away should diminish it, but it remained constant. If it were earthly interference, perhaps it would change at different times of day, or as they pointed to different parts of the sky. But it didn't. It was the same persistent hiss, no matter what they did. They even considered whether seagulls, or other animals, might have somehow been contributing. The lab was not far from the coast, after all. And sometimes, animals can cause unexpected issues. One suspicion fell on a pair of pigeons that had been roosting inside the horn antenna. The birds had left behind a layer of droppings inside the metal throat of the instrument, described rather delicately by the scientists as a white dielectric material. Penzias and Wilson gently evicted the feathered squatters and cleaned out the antenna as best they could, hoping that removing the pigeons and their contributions would silence the mysterious noise. After cleaning the antenna and shooing away the last of the pigeons, Penzias and Wilson aimed the great horn skyward once more and held their breath. For a moment, they hoped the troublesome hiss would finally be gone. They waited quietly as the data came in. To their surprise and dismay, the background hum was still there, just as steady and strong as before. No matter what they did, it seemed the sky itself was humming at them. For days afterward, the two scientists tried everything else they could think of to pin down or eliminate the stubborn noise. They double-checked every circuit and connection in the system. They pointed the antenna at different times of day and toward different parts of the sky, testing if the hiss would change or fade. They even considered the slight glow of microwave energy from the warm ground and atmosphere, subtracting those effects. Yet nothing made the slightest difference. The low, steady hiss persisted, as though the entire sky were just a bit warmer than expected. By now, the scientists were truly perplexed. It was as if the entire sky was simply warmer than expected by a few degrees, and this warmth was manifesting as microwave noise in their receiver. After exhausting the obvious explanations, Penzias and Wilson began to suspect they had stumbled onto something extraordinary, something beyond the usual sources of radio interference. Around the same time, unbeknownst to Penzias and Wilson, a group of physicists not far away at Princeton University were preparing to hunt for exactly such a signal. These researchers, led by Robert Dicker, had been considering an old theoretical prediction, that the early universe's fireball should have left behind a detectable glow. Dicker and his colleagues had not yet made their own detection, but they were gearing up to look for the faint afterglow of the Big Bang. They estimated it would appear as a low-level microwave background permeating space, around a few degrees above absolute zero. As it happened, Arno Penzias mentioned their puzzling noise to an astronomer friend, seeking any insights. During that conversation, he learned that over at Princeton, only some 30 miles away, a team of scientists was actively preparing to search for just such a signal from the early universe. In a flash, Penzias realized what they might have stumbled upon. Perhaps the persistent hiss was not a flaw or earthly interference at all, but the very cosmic afterglow that the Princeton group was anticipating. Penzias and Wilson quickly got in touch with Robert Dicker's team at Princeton to share their observations and ask for their thoughts. When the Princeton scientists heard the details, a uniform microwave noise present in every direction, corresponding to a temperature of just a few degrees above absolute zero, they recognized it immediately. This was no ordinary background static. In fact, upon learning of the discovery, Robert Dicker is said to have turned to his colleagues and quipped, "Well, boys, we've been scooped." The signal his group intended to find had already been picked up by two radio astronomers who stumbled on it while trying to eliminate an inexplicable noise. Soon, the two teams met and compared notes. Penzias and Wilson had meticulously measured the excess noise and found that it corresponded to a temperature of roughly 3.5 K, remarkably close to what the Big Bang theory predicted for a remnant glow. The noise was uniform across the sky, just as one would expect for a cosmic background. There was no doubt now. They had detected the cosmic microwave background, the very afterglow of creation itself. In 1965, they published their discovery in a short paper, modestly describing the excess antenna temperature they observed. In a companion paper, Dicke and his collaborators discussed the interpretation that this was the relic radiation from the primordial fireball of the Big Bang. The news sent ripples of excitement through the scientific community. Here was concrete evidence that the universe did indeed begin in a hot, dense state, that it had a beginning in time. The cosmic microwave background was a smoking gun for the Big Bang theory, and its accidental discovery effectively settled a long-standing debate. Up until then, some scientists had championed an alternative idea, the steady-state theory, which proposed the universe had no beginning and was always roughly the same over time. But the existence of a pervasive cosmological afterglow, precisely what the Big Bang model predicted, and the steady-state model did not, provided dramatic confirmation that our universe had a hot, explosive origin. Overnight, the cosmic microwave background moved from a theoretical speculation to solid fact, and cosmology entered a new era of confidence in the Big Bang. For Arno Penzias and Robert Wilson, the discovery was as surreal as it was profound. Imagine the moment when they first comprehended what they had found. That faint whisper in their big antenna was the echo of the birth of the universe. It was a transformative realization. These two radio astronomers, troubleshooting a nagging noise, had unwittingly tuned in to the reverberation of the creation of everything. In the years that followed, accolades poured in. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for their landmark discovery. Their names became forever linked to one of the most important scientific findings of the 20th century. But beyond the honours and headlines, what truly mattered was what the discovery opened up for science. Now that the cosmic microwave background had been detected, a new window onto the early universe was flung wide open. At last, we could begin to read that cosmic baby picture that had been hidden in the sky. The detection confirmed that this ancient light was real, and it beckoned researchers to study it further, to tease out the wealth of information it carried about the universe's infancy. In the wake of the discovery, scientists around the world grew eager to measure the cosmic background radiation in greater detail. Penzias and Wilson had found the CMB almost by accident, measuring its overall presence and temperature. The next step was to go beyond simply hearing this cosmic whisper. Scientists wanted to actually map it, to listen for any subtle changes or patterns in its tone across the heavens. If this was indeed the baby picture of the cosmos, then hidden in the faint blotches and freckles of that picture could be answers to some of cosmology's deepest questions. How did the matter in the early universe distribute itself? What tiny fluctuations eventually grew into galaxies and clusters? Could we learn the true age and shape of the cosmos from this light? The accidental discovery under the stars had given humanity the key to a cosmic time capsule. With that key in hand, researchers prepared to unlock more secrets. The challenge ahead was significant. The cosmic microwave background is extremely uniform, varying only by tiny fractions of a degree in different directions. Detecting those minuscule differences would require instruments of unprecedented sensitivity and clarity. Yet the promise of what could be learned drove scientists onward. The journey that began with a puzzling hiss in a New Jersey antenna would continue with ambitious efforts to map the ancient light across the entire sky, unveiling a detailed portrait of the infant universe. Detecting the cosmic microwave background was only the beginning. Once scientists knew that this ancient light permeated the universe, they were eager to explore it more deeply. Penzias and Wilson's initial discovery had measured the overall presence and temperature of the cosmic background, confirming that it was indeed there, smooth and steady. But an important question remained. Was this background light perfectly uniform? Or were there tiny variations hidden within it? Did the early universe's afterglow have any faint pattern? Some spots slightly warmer or cooler that could tell us more about how the cosmos began to form structure? According to theory, the primeval fireball that released the CMB would not have been absolutely featureless. There should have been minuscule ripples in the density of matter and energy, slight irregularities in the otherwise even spread of the hot plasma. Over the vast expanses of time, those tiny irregularities would grow under gravity, eventually seeding the galaxies, clusters, and cosmic structures we see today. If the early universe had been completely smooth, there would be no gravitational wells to form stars and galaxies later. So cosmologists were confident that the CMB, if measured with enough precision, would exhibit very slight variations in temperature from point to point on the sky. Finding those slight variations became a top priority. It was like looking for faint freckles on the face of an otherwise smooth cosmic glow. However, detecting such freckles was a formidable challenge. The cosmic microwave background, as Penzias and Wilson observed, is extremely uniform, the same to within a few parts in 100,000. Imagine trying to measure the temperature of a vast ocean and detecting differences of just a few thousandths of a degree between one region and another. It required extraordinary precision and careful control of any potential interference. Early attempts in the late 1960s and 1970s, often using high-altitude balloons or ground-based radio telescopes, yielded no clear detection of variations. The instruments of that era just weren't sensitive enough, and the faint cosmic ripples were drowned out by other sources of noise. It became increasingly clear that to uncover the secrets hidden in the CMB's uniform glow, scientists would have to take their detectors above the distorting effects of Earth's atmosphere and design experiments of unprecedented sensitivity. That realization led to one of the landmark projects in cosmology, the Cosmic Background Explorer, or COBE for short. Launched by NASA in 1989, COBE was a dedicated satellite mission with the ambitious goal of measuring the cosmic microwave background in detail. It carried instruments designed both to take the spectrum of this ancient light and to map its tiny fluctuations across the sky. COBE quietly scanned the heavens from its perch above Earth's atmosphere. Each day, it gathered a few more precious photons of ancient light, slowly building up the most detailed picture yet of the infant cosmos. The scientists on Earth waited patiently as the data accumulated. Then, in 1992, the team behind COBE announced a result that electrified the scientific world. They had detected slight, yet definite variations in the temperature of the CMB across different parts of the sky. After smoothing the data over large patches of sky, they found that some regions were about a few hundred microdegrees, millionths of a degree, warmer or cooler than others. At long last, the freckles on the baby picture of the universe had come into view. This discovery was momentous. The cosmic microwave background was no longer just a smooth backdrop. It had a texture, a subtle pattern imprinted from the early universe. Astronomer George Smoot, one of the leaders of the COBE team, famously remarked that seeing those primordial ripples was like seeing the face of God. That description was poetic, capturing the awe researchers felt. They were glimpsing the very seeds of cosmic structure, the faint imprints of tiny quantum fluctuations from the birth of the universe, blown up to cosmic size by the expansion of space. Those hot and cold spots in the COBE map were the first direct evidence of what theorists had long suspected. The early universe wasn't perfectly uniform. The differences were incredibly tiny, on the order of 1 part in 100,000, but they were real, and they were exactly what was needed to later form galaxies and clusters under gravity's pull. To the world, it was as though humanity had taken its first blurry photograph of the newborn cosmos. That first map of the sky, a patchwork of slightly warmer and cooler spots, captured imaginations and made headlines around the globe. Those hot and cold spots in the Kobe map were not just random speckles, they were the imprint of the universe as a baby, revealing a blueprint of things to come. Kobe's measurements had another triumph as well. It confirmed that the spectrum of the CMB is an almost perfect blackbody. A blackbody spectrum is the hallmark of an object in thermal equilibrium, and the CMB's spectrum matched the theoretical curve with astonishing precision. This meant that the radiation truly was the relic of a hot, dense state in the early universe, and not, say, some collection of radio noise from more recent astrophysical sources. The Kobe satellite's instruments showed that the CMB's intensity peaks exactly as expected for a temperature of about 2.73 K, with no deviations that might hint at any other strange sources. It was a stunning confirmation of the Big Bang model's predictions. In fact, the discovery was so significant that the leaders of the Kobe science team, George Smoot and John Mather, were later awarded the Nobel Prize in Physics in 2006. Smoot was honored for uncovering the anisotropies, the tiny variations, and Mather for measuring the CMB's spectrum. The importance of these findings cannot be overstated. They solidified the Big Bang theory with hard evidence and inaugurated the era of precision cosmology. While Kobe revealed the existence of a pattern, its map of the sky was relatively low in resolution, essentially a blurry first glimpse. The warm and cool spots Kobe detected were on large scales, patches of sky many degrees across. It was like seeing broad brushstrokes of the early universe's texture, but not the fine details. Scientists were eager to zoom in and get a sharper view of those ripples. The finer details held the promise of answering more precise questions. Exactly how much matter, both normal and dark, did those early fluctuations represent? What was the overall geometry of the universe? Was space curved or flat? Did the patterns align with the specific predictions of cosmic inflation? To find out, a higher resolution map was needed. And so, the quest continued with a new satellite, launched at the dawn of the 21st century. In 2001, NASA sent up the Wilkinson Microwave Anisotropy Probe, known as WMAP. This spacecraft, named in honor of David Wilkinson, a pioneering CMB researcher from the Princeton team, was designed to map the cosmic microwave background with far greater clarity than Kobe. WMAP was positioned in a quiet spot in space, at a location called the Lagrange Point 2, about 1 million miles from Earth, where it could observe the cosmos with minimal interference. Over the course of the early 2000s, WMAP scanned the entire sky multiple times, measuring the temperature of the CMB with much higher resolution and sensitivity. When the first detailed full sky maps from WMAP were released, they were breathtaking. The announcement, made in 2003, was greeted with enthusiasm. We had a sharp image of the universe as a baby, only 380,000 years old. The WMAP maps showed the CMB as a rich tapestry of minute temperature fluctuations. Imagine an oval world map projection of the entire sky, speckled with tiny spots of varying color, red and orange blotches indicating regions that are ever so slightly warmer than average, and blue patches for regions that are just a touch cooler. It was as though someone had taken a photograph of the infant universe, and we were now gazing at the pixelated details of that photograph. From these intricate patterns, scientists extracted a wealth of information. The size, distribution, and intensity of the spots in the WMAP map told a precise story about the cosmos. One key finding was that the universe is flat in terms of geometry, meaning, on large scales, space follows the normal rules of Euclidean geometry. This was inferred from the characteristic size of the hot and cold spots. The data also allowed researchers to nail down the age of the universe with remarkable accuracy, about 13.7 billion years, give or take a few tens of millions. Furthermore, the proportions of the universe's ingredients were revealed. It turned out that the cosmos is composed of roughly 5% ordinary matter, the stuff that makes up stars, planets, and us. About 25% dark matter, an invisible form of mass whose gravity helped shape the pattern of the CMB, and about 70% dark energy, a mysterious force driving the accelerated expansion of the universe. These numbers confirmed and refined what other observations had been hinting, painting a cohesive picture of the cosmos. WMAP's observations strongly supported the theory of inflation as well. The statistical distribution of those spots, basically how clump sizes were spread out, matched the signature that a brief epoch of exponential expansion in the universe's first tiny fraction of a second would imprint. It was astonishing to see theoretical ideas about the earliest moments of time being confirmed by data gathered from the sky's gentle microwaves. As the years went by, WMAP continued to operate, improving the clarity of its cosmic portrait with each additional year of data. By the end of its mission, it had mapped the CMB with incredible precision. But the story didn't end there. To push the boundaries of our knowledge even further, an international collaboration led by the European Space Agency launched the Planck satellite in 2009. Planck was the most sensitive and finely tuned CMB observatory to date. It carried sophisticated detectors that were cooled to mere fractions of a degree above absolute zero, ensuring that the instrument's own heat wouldn't interfere with the measurements of the faint cosmic light. When Planck's results came in, with major releases in 2013 and 2015, they represented the culmination of decades of progress. The Planck map of the CMB was like a high-definition version of what COBE had begun and WMAP had refined. The level of detail was breathtaking. Tiny, delicate fluctuations scattered across the sky, down to scales of a few arc minutes, a fraction of a degree. It was as if a once blurry image had become crystal clear. With Planck's data, cosmologists achieved even tighter constraints on the universe's age, revising it slightly to about 13.8 billion years, and on other key parameters like the Hubble constant, the rate of cosmic expansion, and the exact composition of the universe's matter and energy. The fundamental picture of a universe born in a hot Big Bang, structured by inflation, composed predominantly of dark matter and dark energy, and expanding over billions of years was resoundingly confirmed. Perhaps just as importantly, Planck's high resolution allowed scientists to study not just the temperature of the CMB, but its polarization as well, the orientation of the light waves. Put simply, polarization is a measure of how the light waves from the CMB are oriented. It's as if the ancient light not only carries a temperature imprint, but also a faint directional pattern from when it last scattered off matter in the early universe. These polarization patterns carried additional clues about the early universe, potentially even whispering hints about gravitational waves rippling through spacetime during the era of inflation. The full analysis of polarization is complex. In 2014, a team using a specialized telescope at the South Pole thought they had detected a subtle swirled pattern in the CMB's polarization, a possible sign of gravitational waves from the universe's first fraction of a second. For a moment, it seemed another incredible secret had been unveiled. But later analysis showed that much of the signal was actually caused by dust within our own galaxy, underscoring how challenging these measurements can be. Still, the quest continues. Future experiments are being designed to search even more carefully for those primordial gravitational whispers in the polarization of the CMB. Looking at the CMB maps from COBE to WMAP to Planck, one can't help but feel a sense of wonder. We have gone from hearing a faint, featureless hum to seeing an exquisitely detailed baby picture of our universe. The mottled pattern of the cosmic microwave background is like a cosmic blueprint, a record of the universe as a newborn, containing the seeds of all future structures. Tiny differences in temperature represent slight differences in density back then. The denser spots would eventually draw in more matter and grow into galaxies and clusters of galaxies, while the slightly less dense spots would become the vast voids between galaxy clusters. In the CMB map, we are essentially observing the primordial melody that would later orchestrate the arrangement of galaxies in the sky. It is remarkable that so much information, the age, shape, and composition of the universe, and even clues about its earliest moments, came from analyzing the faintest whispers of light. The scientists and engineers who built these experiments had to measure temperature differences of just a few 10 millionths of a degree, an almost unimaginable precision. Yet they succeeded, transforming what was once a mysterious hiss into a rich cosmic narrative. By delving into the details of this ancient light, researchers have confirmed much of our cosmological model. But they have also encountered new puzzles. For the most part, the patterns in the cosmic background fit our expectations and have validated our theories. However, amid the tapestry of tiny spots, they noticed a few anomalies, subtle irregularities that did not quite fit the random noise. For example, one side of the sky showed a slightly different average temperature than the other, a curiosity that intrigued researchers. One in particular drew considerable attention, a region of the sky that appears unusually cold, beyond what random fluctuations would likely produce. As our view of the infant universe sharpened, this unexpected cold spot emerged as a small mystery of its own, hinting that the cosmic microwave background might hold even more surprises than we initially thought. As scientists delved into the detailed maps of the cosmic microwave background, they found that most of the tiny temperature fluctuations were just as theory predicted, random, subtle speckles that fit the standard model. There were a couple of curious large-scale features that drew interest, such as a slight asymmetry in the distribution of fluctuations on opposite hemispheres of the sky, but nothing too alarming. However, one area of the sky caught their attention for being a bit too cold. It was as if, on an otherwise evenly dappled painting, someone had pressed a thumb and smudged one spot a shade darker. This region, which came to be known simply as the cold spot, appeared as a noticeably cooler patch in the CMB's all-sky map. It wasn't something visible to the naked eye, of course. You'd only see it in the false colour maps where blue indicates cooler than average areas. But in those maps, the cold spot stood out like a deep blue bruise on the cosmos. The cold spot is located in the southern hemisphere of the sky, roughly in the direction of the constellation Eridanus. It spans a sizable patch of the sky, much larger than a typical fluctuation. When the WMAP satellite first produced its full sky map in the early 2000s, researchers noticed this large blue region that was cooler than the average CMB temperature by an unusually large amount. At first, there was some hesitation. Could this be an artifact of the data? Perhaps a glitch in the instrument, or some interference along the line of sight. The WMAP team double and triple checked their results. They compared data from different years and different observing angles. Yet the cool patch persisted. It became clear that this was not a mistake. It was a real feature of the cosmic background. Statistically, the cold spot was an oddball. The CMB's temperature variations are expected to follow a very specific random distribution. While small hot and cold spots of various sizes are normal, the chance of having such a large region that is significantly colder than average is low. Think of tossing a handful of sand on a table. You expect a mix of small clumps and gaps, but finding one big clear gap in the middle would be surprising. By the initial estimates, the cold spot was so pronounced that only a few out of thousands of simulated CMB maps generated under the standard cosmological model produced anything similar. Some analyses suggested there was less than a 2% probability of a feature like the cold spot occurring by random chance. In other words, it was something that made cosmologists raise their eyebrows. The cold spot's temperature isn't cold in any everyday sense. Space in that direction is still just the same frigid 2.7 K background, only slightly colder by about 1 part in 100,000. We're talking differences on the order of a few tens of microkelvins, millionths of a degree. But those tiny differences carry big meaning in cosmology. The cold spot was roughly 70 microkelvins cooler than the surrounding average, a noticeable dip in the context of CMB fluctuations. In the WMAP maps, which had a resolution of about half a degree, the cold spot encompassed a region many degrees across. Later, when the Planck satellite, with its higher resolution and sensitivity, observed the same region, it confirmed the cold spot's presence and characteristics with greater confidence. Planck's data put to rest any lingering doubts that this cool blotch might have been a WMAP error. The cold spot was undeniably real. The existence of this odd, cold region sparked a flurry of scientific curiosity. What could cause such a large, cool area in the otherwise statistically uniform early universe? Cosmologists began to brainstorm and test various ideas. One straightforward possibility was that the cold spot might just be an unlikely fluke, a statistical anomaly in an otherwise well-understood random field. After all, low probability events can happen by chance. If you roll the cosmic dice enough times, in this case across the 41,253 square degrees of sky, occasionally you get an unusual result. Some researchers lean toward this interpretation, essentially saying, yes, it's unusual, but it could just be the universe playing a statistical trick on us. If that were true, the cold spot wouldn't necessarily point to any new physics. It would just be a rare, but ultimately unremarkable, coincidence, once we accept the odds. Other scientists wondered if there might be something more concrete and physical behind the cold spot. One idea involved structures between us and the cosmic microwave background. Remember that the CMB light has travelled for more than 13 billion years to reach us, and along the way it has passed by galaxies, clusters, and vast voids, the large-scale structure of the universe. As CMB photons journey through these structures, their energies can be slightly altered by gravity, a phenomenon known as the integrated Sachs-Wolf effect. If a CMB photon passes through a huge supervoid, an enormous region of space with far fewer galaxies than average, it can lose a bit of energy. Essentially, as it enters the void, it gains a little energy falling into the region's gravitational well. But as it exits, the universe's expansion means it doesn't fully regain that energy. The result is the photon comes out a tad cooler than it went in. So, could the cold spot be the imprint of a gigantic supervoid lying in that direction of the sky? In the mid-2010s, astronomers went looking for evidence of this. Surveys of galaxies in the region of the cold spot did indeed hint at something interesting. A relatively empty patch of the universe, perhaps a few billion light-years across, roughly aligned with the cold spot's position. In 2015, a team of researchers, led by Istvan Sapudi, announced the discovery of what they called a supervoid, an expansive region about 1.8 billion light-years in diameter, where galaxy density is unusually low, sitting in front of the cold spot's coordinates. This supervoid, they proposed, could account for some of the cold spot's temperature drop by draining energy from the CMB photons that traverse it. The supervoid idea was intriguing. It provided a tangible structure that we could observe with galaxy surveys, and it made intuitive sense. A big emptiness could leave a cool fingerprint on the CMB. However, as more data were analysed, questions arose about whether the void was truly large or deep enough to explain the full effect. Some studies suggested that while the void, if it exists as proposed, might contribute to the cooling, it likely couldn't account for the entire 70 microkelvin dip. The cold spot might be only partially due to an intervening supervoid, meaning there could be more to the story. This opened the door to even more exotic hypotheses. When confronted with a cosmic mystery that doesn't have an obvious explanation, scientists sometimes indulge in more speculative ideas, not as confirmed theories, but as what-if propositions to explore. One of the more imaginative proposals was that the cold spot could be evidence of something as profound as a collision with another universe. In the speculative multiverse scenarios of inflationary cosmology, our Big Bang might not have been the only one. If our expanding bubble universe had at some point in the distant past brushed up against another bubble universe, it could, in theory, leave an imprint on the CMB. Perhaps a disk-like anomalous region, maybe a little cooler or hotter than its surroundings. Could the cold spot be such a bruise from a cosmic fender bender between universes? It's a fascinating idea, almost science fiction in flavour, and it grabbed headlines for a time. Researchers analysed the shape and profile of the cold spot to see if it fit the predictions of a bubble collision model. The results were inconclusive. It's hard to distinguish a multiverse collision fingerprint from other, more mundane explanations using just our one sky. Most cosmologists view this multiverse collision idea as a very long shot, an intriguing possibility, but with scant evidence. After all, extraordinary claims require extraordinary proof, and so far, the cold spot hasn't provided evidence strong enough to favour this interpretation over more conventional ones. Still, it's a testament to human curiosity that even a slight anomaly in the sky can lead us to ponder things as profound as the existence of other universes. Between the straightforward, it's just a fluke explanation and the far-out multiverse scenario lie some intermediate possibilities as well. Some have proposed that perhaps the cold spot could be a sign that the early universe had slightly different conditions in that region, maybe a localized feature or a quirk of how inflation occurred that produced an extra-large fluctuation. Others have considered whether there might be unknown physics at play affecting the CMB on large scales. So far, none of these ideas has gained enough support to be considered likely. The standard cosmological model, which has been enormously successful, doesn't predict a cold spot, but it doesn't strictly forbid one either. As of now, the consensus leans towards the cold spot being a statistical anomaly, basically a rare roll of the cosmic dice. The Planck satellites analysis, which was the most precise to date, found that the cold spot's unlikeliness was somewhat less extreme than initial estimates, depending on exactly how one defines cold spot. It's still an odd feature, perhaps one of the oddest in the CMB, but it might not require new physics to explain. If we had the ability to observe many different universes, each with their own CMB, maybe around 1 in 50 or 1 in 100 would have a patch like our cold spot somewhere in their sky. In that sense, we could just be living in one of those universes where an unlikely thing happened by chance. Yet, the cold spot continues to intrigue. It reminds scientists that even in this golden age of precision cosmology, when a simple model with just 6 basic parameters can describe the universe's evolution so well, there might still be wrinkles and surprises left to discover. The cold spot keeps us humble. It's a gentle nudge from the cosmos, saying, there are things you don't fully understand yet. And that's a good thing, because it means there's still mystery in the universe for us to chase. When we gaze at the color-coded maps of the cosmic microwave background, the cold spot is a subtle feature. One blue blotch in a tapestry of red, yellow, and blue speckles. To a casual observer, it might not look particularly significant. But knowing what it represents, we can't help but wonder about it. Is it an enormous void casting a chill shadow on the ancient light? Is it a statistical fluke that we're lucky or unlucky to witness? Or is it the telltale scar of something extraordinary in the prehistory of our universe? For now, we don't have a definitive answer. What we do have is the enduring image of this cold patch, imprinted in the oldest light in the universe, challenging us to explain it. Future surveys of galaxies and large-scale structures might pin down the supervoid explanation more clearly, or perhaps rule it out. Upcoming cosmological observations and more refined analyses could offer new insights, or even reveal other subtle anomalies that put the cold spot in context. It's even possible that as our theories evolve, we'll come to see the cold spot not as a problem, but as a natural result of some refined model of cosmology. In the meantime, the cold spot sits quietly in the sky, a faint echo of something, we know not what, from billions of years ago. It invites us to ponder and to investigate. In the grand scheme, it doesn't overturn the successes of the standard model of cosmology, but it adds a touch of mystery at the edges of our cosmic map. And for a field that deals with the origin and fate of the entire universe, a little mystery is a welcome reminder that the story isn't finished. Our journey through the cosmic microwave background, from its primordial whisper to its detailed mapping, and finally to this curious cold spot, highlights how far we've come in understanding the invisible universe and how much there still is to learn. The invisible becomes visible through our instruments and our insight, and as it does, it both answers age-old questions and raises new ones. In the faint, cool glow of the cold spot, we can sense that the universe has not given up all its secrets. There are deeper depths to plumb and subtler messages to decipher in the whispers of ancient light. And so we end this part of our journey, wrapped in the calm wonder of what has been revealed, and quietly excited for the mysteries that remain just beyond the visible, in the whispering dark of the cosmos. In the silent canvas of the cosmic night, a faint afterglow whispers secrets from the dawn of time. This ghostly light, the cosmic microwave background, bathes the entire sky with an almost uniform glow. To human eyes, it's invisible and unremarkable, but sensitive instruments reveal a delicate mottling of warmer and cooler patches. These tiny temperature ripples in the Big Bang's afterglow are the fingerprints of the infant universe, usually following patterns our theories expect. As a matter of fact, if you ever tuned an old-style television to a blank channel, a portion of the static on the screen was caused by this very afterglow of the Big Bang, discovered by accident in the mid-20th century as a pervasive radio hiss coming from all directions. The cosmic microwave background quickly became a cornerstone of cosmology. It is the cooled, faint echo of the primeval fireball, now spread thinly across space. For decades, scientists have mapped and studied this background, finding it remarkably uniform, but sprinkled with tiny variations that held clues to how galaxies and clusters would one day form. By the early 2000s, technology had advanced enough to map these delicate ripples with unprecedented precision. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, spent years surveying the sky, recording the temperature of the microwave background at millions of points. The resulting all-sky portrait of the infant universe was a triumph, a mottled pattern of minuscule hot and cold spots that matched the predictions of the Big Bang theory and cosmic inflation to exquisite detail. And yet, amid this triumph, that map also revealed an odd feature that no one had expected. Yet hidden in this subtle celestial tapestry lies a peculiar blemish that has both puzzled and intrigued scientists. When astronomers first mapped this primordial light in exquisite detail, they discovered an unexpectedly large cold region, a spot colder and bigger than anything they anticipated. It was as if the cosmos had placed a single deep blue brushstroke on an otherwise gently speckled background. This discovery, quietly announced in the early 2000s, would soon ripple across the cosmological community as a profound mystery. This so-called cold spot emerged from data gathered by a satellite scanning the heavens for the Big Bang's faint afterglow. Launched to measure tiny variations in the cosmic microwave background, the probe faithfully charted the subtle highs and lows of that ancient light. Amid the data, in the direction of the constellation Eridanus in the southern sky, a cool patch stood out. It wasn't just slightly cooler, it spanned a vast region and dipped in temperature more deeply than surrounding areas. Scientists double-checked the maps, recalculating and reprocessing to ensure it wasn't a mistake or a stray interference from closer to home. But the cold patch persisted, clear and unmistakable. For context, the entire cosmic background is only a few degrees above absolute zero. The differences across the sky are measured in mere millionths of a degree. Finding any spot significantly colder than the average is already notable. But this cold spot was about a few dozen millionths of a degree colder, a seemingly minuscule difference, yet enormous in the context of cosmic background fluctuations. And crucially, it covered an unusually large patch of sky, roughly circular, spanning a region many times wider than the full moon's face. In a map where typical speckles are much smaller, this broad, cold blotch immediately captured astronomers' attention. The cold spot's discovery felt like uncovering a quiet secret written into the fabric of the universe. It wasn't something predicted or sought. It emerged from the data unbidden. Initially, it might have been easy to overlook as just another faint smudge. But as researchers dug deeper, they realized its significance. According to the standard cosmological models, which had been enormously successful in explaining the other variations in the microwave background, a cold region of this size and depth was highly improbable. The cosmos seemed to be pointing at an anomaly, inviting curiosity. News of the cold spot travelled slowly at first, confined to scientific meetings and papers. But it carried a weight that grew heavier with each discussion. Could it be a sign of some error in the measurements? Or perhaps an artifact of how the data were being analysed? Scientists are trained to be skeptical, especially of surprising findings. Many held their breath, waiting for confirmation or refutation, unsure whether this chilly patch was a genuine feature of the universe or a mirage born from noise. Before long, this mysterious spot earned a name that stuck. The cold spot. Unimaginative, perhaps, but apt in its simplicity. It became a topic of whispered conversations in cosmology departments around the world. What could cause such a feature? Was it simply a rare fluke in the random pattern of primordial fluctuations? If so, it would be an astonishing fluke, an almost 1 in 100 kind of event. Or was it a clue pointing to physics beyond our current understanding? The possibilities stirred both caution and excitement. In those early days, as the cold spot first came to light, the scientific community approached it with a mix of wonder and wariness. On one hand, anomalies are the seeds of discovery. Throughout history, unexpected observations have often led to breakthroughs. On the other hand, anomalies can also vanish under scrutiny, revealed as miscalculations or statistical quirks. With that in mind, researchers prepared to scrutinize this cosmic oddity from every angle, determined to discern truth from illusion in the faint echoes of creation, The first step in unraveling the cold spot's mystery was to verify that it was real. Extraordinary claims require extraordinary evidence, and an unexpected blemish on the cosmic background certainly qualified as extraordinary. Researchers pored over the data from the satellite that had revealed the cold spot, looking for any sign of error or bias. They examined multiple years of observations and applied different analysis methods. Each time, the cold patch in the sky refused to disappear. It persisted as a distinct feature, suggesting it was not a fluke of instrumentation or a hiccup in data processing. By the time several years of cosmic microwave background measurements had been analyzed, the cold spot had entrenched itself as an undeniable reality in our map of the early universe. It is worth noting that when the cosmic microwave background was first detected, researchers went to great lengths to rule out trivial causes. Famously, they even cleaned out pigeon droppings from their radio antenna, thinking the bird nests might be the source of the mysterious noise. In the end, that noise proved to be the Big Bang's afterglow. In the case of the cold spot, no such mundane explanation could be found. This was no stray interference or simple observational glitch. It was imprinted in the cosmos itself. Still, confirmation only deepened the puzzle. If the cold spot was genuine, what were its implications? Scientists quantified how unlikely it was under the prevailing theories. By running elaborate simulations of the universe, they tried to gauge the odds of such a large, cold region popping up by chance. The answer that came back was tantalizing. The cold spot was an extremely rare event in those simulations. One analysis suggested there might be only a 1 or 2% chance of a random occurrence producing a patch so cold and so large. This hinted that something more than chance could be at play. However, a few percent is not zero. Rare coincidences can happen. Thus, the scientific community found itself in a delicate dance between open-minded wonder and cautious skepticism. According to the theory of cosmic inflation, which describes how the universe expanded in the earliest fraction of a second, the temperature fluctuations in the CMB should follow a very specific random pattern. They ought to be what scientists call Gaussian, meaning no particularly large deviation is expected beyond a certain scale. A feature as prominent as the cold spot wasn't anticipated by these simple models. If it truly cannot be explained by chance under standard inflationary theory, it might hint at new physics at play during those primordial moments, an enticing possibility that cosmologists could not ignore. Debate sparked in journals and conferences about the true significance of this anomaly. Some researchers argued that our methods of searching for unusual spots might be exaggerating its importance. After all, if one combs through vast amounts of data looking for the biggest oddity, one is guaranteed to find something that appears anomalous, even if it's just by luck. Was the cold spot simply the inevitable strange one among billions of normal fluctuations? Perhaps, some said, we shouldn't be too surprised to find an outlier in a universe this vast. Others pointed out that even considering those odds, the cold spot remained a conspicuous outlier worthy of attention. It wasn't just a tiny statistical hiccup. It was the largest such deviation we'd seen in the primordial sky. To bolster confidence, an even more precise all-sky survey was eagerly awaited. In 2013, the European Space Agency's Planck satellite delivered its own high-resolution map of the cosmic microwave background. With finer detail and improved sensitivity, Planck was the ultimate test of the cold spot's existence. If the patch vanished or changed drastically under Planck's scrutiny, it might indicate the anomaly was a trick of earlier data. But when the Planck results came in, there it was, the cold spot, as cold and as large as before. staring back at us from the newborn universe. Planck's confirmation dispelled lingering doubts that perhaps the earlier map had been deceiving us. The anomaly was real, etched into the cosmic background with the same perplexing profile. This confirmation was both reassuring and perplexing. It meant the cold patch was truly imprinted on the sky itself, not an artifact of measurement. Yet by affirming the anomaly's reality, Planck had deepened the mystery. The cosmos had drawn our attention to a genuine puzzle written in its oldest light, begging for an explanation. With multiple confirmations in hand, scientists grew more confident in exploring explanations. Attention turned fully to the question of why this region was so cold. Every possibility was on the table, from mundane to mind-bending. On the cautious end, one might suspect an unaccounted foreground effect, something between us and the Big Bang's light that made the spot seem colder. Could there be a cloud of cold gas or dust in our galaxy or nearby that cast a subtle shadow? Early checks found no obvious local culprits. This cold patch was not due to any known contamination. The sky in other wavelengths, like visible light or radio waves, didn't show a bright object or anything straightforward that could mess with the microwave readings. Other explanations ventured into new physics. One idea put forth was that the cold spot might be a sign of a primordial cosmic texture. In certain theories of the early universe, as the hot plasma of the Big Bang cooled and fundamental forces separated, defects could form, a bit like cracks appearing when water freezes to ice. A cosmic texture would be one such defect, an exotic knot in the fabric of spacetime left over from those first moments. If a texture had indeed formed in our universe's youth and lay in the direction of Eridanus, it might have imprinted a cold region on the microwave background by subtly distorting the energy of the primordial light. This idea was highly speculative, but undeniably exciting. Detecting a cosmic texture would reveal new aspects of physics not captured in the standard cosmological model. The very possibility stirred imaginations, even as concrete evidence remained elusive. If a cosmic texture were responsible, it could leave a distinctive signature. Scientists have searched the CMB data for hints of such a relic, perhaps a specific pattern around the cold spot or telltale polarization signals. But so far, the evidence is inconclusive. The texture idea remains on the table, intriguing but unproven, a reminder of how little we still know about those first moments after the Big Bang. It is a hypothesis that invites more data and careful analysis, keeping the door open for new physics while refusing to claim victory without proof. Meanwhile, other scientists approach the cold spot with a healthy dose of skepticism. They re-examined the evidence and noted that the cold spot's prominence partly depends on how it's defined. Intriguingly, the cold area is surrounded by a slightly warmer, ring-like halo. When a specialized filtering technique was applied to the data to accentuate such patterns, the contrast between the frigid center and its warmer ring made the anomaly stand out sharply. Critics wondered if this method had made the spot seem more exceptional than it truly was. If one looked at the raw sky map without these enhancements, the cold spot was still present. Even so, the microwave background is full of peaks and dips, meaning this cold area might not be as unique as it appeared after filtering. This perspective kept many researchers cautious. Was the cold spot truly extraordinary on its own, or had our analysis techniques amplified its importance? Such questions tempered the excitement with a reminder of how tricky cosmic data can be. Despite these debates, interest in the cold spot only grew. The anomaly had passed the first critical tests of legitimacy, and that meant it deserved serious attention. Imaginative theories proliferated alongside sober analyses. For every paper arguing it was just a statistical fluke. Another offered a novel hypothesis for its origin. Whispers of new physics filled the halls of academia. Some even floated the idea that our universe had brushed against another universe in its infancy, a truly radical notion that would place the cold spot as evidence of a cosmic collision across reality itself. Such ideas were controversial and far from proven, but the fact they were being discussed at all underscored how exceptional this cold patch appeared. The period following the cold spot's discovery was thus one of intense scrutiny and spirited debate. Gradually, a consensus emerged on at least one point. The cold spot was real, and not an artifact of errors. Accepting that, the focus could shift to measuring and understanding it in detail. If this cosmic bruise was going to yield its secrets, scientists would have to probe it more deeply, quantifying its properties, searching for any hints of what might lie between us and that patch of ancient light, and determining just how far beyond the ordinary it truly was. With that in mind, researchers set out to measure the unusual nature of the cold spot, hoping that numbers and observations might succeed where speculation alone could not. If theory alone couldn't easily explain the cold spot, perhaps data could. They asked, what, if anything, is special about that region of the sky beyond the microwave background itself? Could something in the intervening space be responsible for the chill? To find out, astronomers scrutinized the cold spot's coordinates in other maps of the universe. They looked at surveys of galaxies, clusters, and intergalactic gas, effectively peeling back the layers of the cosmos between us and the source of the microwave background. One early clue emerged a few years after the cold spot's discovery. In 2007, a team examining a map of distant radio galaxies noticed something intriguing. The counts of galaxies seemed lower than average in the cold spot's direction. It was as if that patch of sky had less matter in it, potentially a vast cosmic void. This was an exciting hint, but there was a catch. The radio survey could show how many galaxies were seen in that area, but not how far away they were. For all the team knew, those galaxies might simply be arranged differently along the line of sight, not leaving a true void. Still, the suggestion that a huge empty space could lurk in front of the cold spot set minds racing. If real, such a void might be exactly the kind of structure that could cool down the background's glow. Voids themselves were already familiar to astronomers. Over large scales, the universe looks like a cosmic web. Galaxies gather in clusters and filaments, and between them lie voids, vast regions with far less matter. One famous example, the Boötes void, spans hundreds of millions of light-years with hardly any galaxies. Yet the void hinted at in the cold spot's direction promised to dwarf even that enormous expanse. If it truly existed, it would be among the largest, most rarefied holes in the cosmic web ever found. Building on the radio survey hint, astronomers set out to confirm whether a supervoid, a void of unprecedented size, really coincided with the cold spot. This was a daunting task. Mapping matter in the universe is like surveying an invisible landscape. Galaxies are the beacons used to trace structure. Where there are fewer galaxies, one infers emptiness. But one must measure the distances to those galaxies to ensure that an apparent gap on the sky is an actual cavity in space. Measuring the distances to galaxies is painstaking, often requiring detailed analysis of each galaxy's light. For a region this large, gathering that depth information was no small feat. In the late 2000s and early 2010s, large-scale galaxy surveys and all-sky observations were advancing rapidly. Teams began combing through these datasets, focusing on the expanse around the cold spot. They pooled data from multiple telescopes and wavelengths, including visible light observatories scanning for galaxies and space-based infrared telescopes mapping out faint, distant clusters. Bit by bit, the picture became clearer. After years of investigative sky mapping, the breakthrough came. In the mid-2010s, an international group of astronomers announced evidence of a tremendous supervoid aligned with the cold spot. Using data from telescopes in Hawaii and satellite observations, they identified a region about 3 billion light-years away that contains far fewer galaxies than expected. This void is not a small dip in density, it is staggeringly vast. By their estimates, it stretches roughly 1.8 billion light-years across, making it one of the largest voids ever recorded. To put that in perspective, a void of this size is an immense chunk of the cosmos, so large that you could line up about 20 Milky Way galaxies end to end to span just 1% of its width. Discovering such a gigantic cosmic emptiness was remarkable in its own right. That discovery cemented the idea that the cold spot's anomaly was indeed connected to a massive structure in the cosmos. What would it be like to drift through such a void? In its center, the nearest galaxies would be staggeringly far away, mere faint smudges of light on the cosmic horizon. The usual tapestry of galaxies and clusters that fills the universe would be largely absent here. In every direction, you would see mostly the blackness of intergalactic space, punctuated only by a few distant glimmers. It would be a realm of nearly pure darkness, a truly lonely expanse of the cosmos. And yet this immense emptiness, invisible to the eye, left an imprint. It subtly cooled the glow of the Big Bang as it passed through, creating the cold spot we observe. What are the odds of such a void existing? Cosmological models predict the distribution of structure, the voids and filaments and clusters, in our universe. A void as huge as the one found in the cold spot's direction would be a very rare beast. Perhaps only a handful of comparably sized voids might arise within the entire observable cosmos. Finding one is like finding a cavernous hole in an otherwise bustling cityscape of galaxies. This rarity meant that the cold spot's mystery now had an enticing potential explanation rooted in known physics. Perhaps an extraordinarily large void between Earth and the cosmic microwave background is responsible for the unusually cold patch of sky. To many cosmologists, the discovery of such an immense void was startling, but not impossible. It pushed the boundaries of what our standard model of structure formation would anticipate, yet remained just within the realm of plausibility. In other words, the cold spot's void was a surprise, but not an outright contradiction of known physics. Its existence highlighted how our universe can occasionally produce extremes that keep theorists on their toes. With the supervoid mapped and measured, researchers calculated how much of the cold spot's temperature drop could be explained by it. The void's underdensity and enormous size mean it can indeed imprint a cooler region on the CMB via the integrated Sachs-Wolf effect. The numbers were encouraging. Such a void could account for a significant fraction of the cold spot's anomalous chill. Light crossing this cosmic chasm would arrive a bit fainter in energy, just as the cold spot reveals. It was a gratifying moment for many, an instance of an observational clue leading astronomers to discover a new physical structure that in turn helps explain the observation. In a sense, the cold spot had guided us to uncover one of the universe's largest hidden features. However, the story doesn't end with a tidy resolution. Even though the supervoid provides a plausible explanation, it might not completely settle the case. The void's effect, while substantial, may not fully explain the extreme coldness of the cold spot all by itself. Some calculations suggested that the void's presence only partially accounts for the temperature dip, meaning the cold spot could still be a bit colder than the void alone would predict. This implies that while the void is likely a key piece of the puzzle, there may be additional factors at play, or the cold spot might still be somewhat special as a statistical fluke layered on top of the void's influence. On the other hand, some researchers caution against declaring the mystery solved too soon. It could be that the cold spot's full story involves a combination of factors. Perhaps an unlucky, but not impossible primordial fluctuation made that patch of the CMB a little colder initially, and then, by sheer chance, that line of sight also contains an enormous void amplifying the effect. In that scenario, we have a bit of coincidence layered on physics. Neither the fluctuation nor the void alone would be too extraordinary, but together, they produce an outlier like the cold spot. Untangling these contributions is challenging, and scientists continue to analyze data from new sky surveys and refined CMB maps to pin it down. Measuring the unusual nature of the cold spot has thus been a journey in both senses. A journey across billions of light years in space, and a journey of scientific discovery. It has led from simply spotting an anomaly in a map to uncovering a gigantic unseen structure in the cosmos. The process showcased the detective work of cosmologists, who must use indirect clues to piece together what's happening across unimaginable distances. Bit by bit, observation by observation, the cold spot's contours became more defined. What started as a curious cold patch transformed into evidence of a vast void, teaching us about the distribution of matter and the effect of dark energy on cosmic light. For many in the field, this is a satisfying outcome. A decade earlier, some had feared the cold spot might be an inexplicable oddball, a thorn in the side of standard cosmology. Now, it seems to largely fit within the framework we have, requiring no drastic overhaul of fundamental theory, but rather highlighting an extreme example of structures that theory did allow, albeit rarely. In confirming the supervoid's existence and its relevance, scientists found reassurance that our cosmological models and the presence of dark energy hold true even in puzzling cases like this. It's a reminder that sometimes the universe's strangest features can still arise from known phenomena when conditions line up just right. It's important to note that this phenomenon occurs only because the universe's expansion is accelerating. If space were not stretching faster and faster under the influence of dark energy, a photon would leave a void with exactly the same energy it entered. Thus, the mere existence of an ISW imprint, like a cool spot linked to a huge void, serves as a subtle confirmation of dark energy's reality. In the cold spot's case, it's as if this anomaly is whispering a reminder of the dark energy permeating our universe. Yet, a sense of mystery remains. The cold spot and its void have not completely quashed the more exotic speculations. The void explains much, but if it falls short of explaining everything, questions linger in the margins. Is there still something genuinely anomalous about the cold spot beyond the void's influence? Could there be a subtle physics effect we haven't accounted for, lurking in that patch of sky? Have we simply yet to refine our measurements enough to close the gap between prediction and observation? These questions keep the cold spot in a state of scientific suspense, a case mostly resolved, but with loose ends that encourage further inquiry. In cosmic terms, such ideas are speculative, but they capture the imagination. If a parallel universe did brush ours, the cold spot might be the only evidence of that encounter, a silent scar from a time before our observable universe expanded and separated from its neighbours. It's a far-reaching hypothesis, bordering on science fiction, but it remains one possibility that researchers keep in mind, until more data can either support or refute it. The multiverse connection to the cold spot stays in the realm of intriguing conjecture. What is clear is that through careful measurement and dogged exploration, we have pushed the cold spot from a total enigma towards a comprehensible phenomenon. We mapped the invisible void that shares its coordinates, and in doing so, turned a spotlight on one of the universe's largest secrets, hidden in plain sight. The act of measuring this unusual cold patch has deepened our understanding of how light and matter interplay across cosmic time. And while it has steered the mystery toward an explanation, it hasn't entirely dispelled the aura of the unexplained. That delicate balance between knowledge gained and questions remaining sets the stage for the next part of our journey, where we ask whether the cold spot truly demands something beyond the ordinary, or if our journey so far has already uncovered the essential truths behind this cosmic curiosity. Far beyond the realm of individual galaxies and clusters, the universe reveals a hidden pattern. Out beyond the scattered islands of galaxies, a secret structure begins to emerge. When we drift further into the darkness between galaxy clusters, the cosmos unveils its grand design. What once seemed like random points of light takes shape as a vast cosmic tapestry. The galaxies trace out filaments and tendrils, threading across space in delicate patterns. And in between these luminous strands lie enormous dark gaps. It is as if they were charting not just the islands of matter, but the dark oceans of emptiness between them. From this perspective, it becomes clear that galaxies are arranged in a cosmic web, extending across unimaginable distances. Gravity draws galaxies into clusters and lines, forming filaments that stretch for hundreds of millions of light years. These filaments outline immense cavities, cosmic voids, like empty bubbles in a foam of cosmic scale. On the grandest scale, the universe is a lacework of matter and emptiness, an almost organic pattern shaped by invisible forces. Intriguingly, when visualized, the cosmic web's appearance has been likened to other complex networks. It resembles the foam of soap bubbles pressed together, and even evokes comparisons to neural structures in a brain. Nature, it seems, repeats familiar patterns on vastly different scales. Beneath this cosmic pattern lies a mysterious foundation. Scientists believe an invisible scaffold of dark matter underpins the cosmic web, its gravity guiding galaxies along the threads. The luminous galaxies we see are like dewdrops clinging to a spider's web, revealing the strands of dark matter that would otherwise remain unseen. Even the vast voids are defined by this presence and absence. In those enormous gaps, both galaxies and dark matter are scarce, creating truly immense expanses of nearly empty space. How did this intricate cosmic web come to be? The story begins in the early universe, which was almost perfectly uniform after the Big Bang, with only tiny fluctuations in density. Over billions of years, gravity amplified those slight irregularities. Regions with a bit more matter pulled in surrounding material, growing into clusters and filaments, while nearby low-density patches lost matter and became emptier. Cosmic voids are essentially the places that were left behind as matter flowed away, the emptied hollows of creation. This process, guided by both visible matter and the dominant invisible dark matter, wove the universe's large-scale structure from an almost featureless beginning. Computer simulations of the universe have vividly shown this web emerging. Cosmologists input the laws of physics and initial conditions into vast computational models, and then watch as they run the clock forward in these virtual universes. The outcome is a very familiar pattern. Matter condenses into strands and clumps, mirroring the filaments and clusters we observe, and enormous voids open up between them. The fact that simulations and observations match so well boosts confidence that our theories of cosmic evolution, including the presence of abundant dark matter, are on the right track. Gravity, acting on dark matter and gas over eons, naturally produces a cosmic web of galaxies and voids, very much like the real one. These cosmic voids are enormous, spanning tens to hundreds of millions of light years across. Remarkably, voids make up the majority of the universe's volume, around 4/5 of space, yet contain only a sprinkling of galaxies. In one of these vast vacancies, a single galaxy might float in isolation, where ordinarily thousands of galaxies would reside. To an observer drifting in the center of a void, the emptiness would feel nearly absolute, with only the faintest glimmers of distant galaxies at the horizon of sight. For much of human history, we had no inkling of this grand cosmic architecture. It wasn't until the late 20th century that astronomers had the tools to map galaxy positions on truly large scales. Many expected that if you surveyed far enough out, the universe would appear homogeneous, with galaxies evenly spread or gradually thinning out. Instead, the first comprehensive maps revealed something far more structured and surprising. In the late 1970s and 1980s, astronomers began measuring galaxy redshifts en masse, each redshift giving the distance to a galaxy, allowing them to plot 3D locations of thousands of galaxies. The patterns that emerged were astonishing. They uncovered features like the Sloan Great Wall, a vast sheet of galaxies hundreds of millions of light years long, and huge voids adjoining it. One survey revealed the Boötes void, an enormous gap nearly empty of galaxies. It was as if the galaxies were painting the boundaries of gigantic bubbles. These discoveries fundamentally changed our understanding of the cosmic landscape. Astronomers at first double-checked their data in disbelief. Could such a huge volume of space truly have so little in it? One of the largest voids ever found, the Boötes void, became legendary for its sheer emptiness. Spanning roughly 330 million light-years in diameter, this void contained so few galaxies that some astronomers dubbed it the Great Nothing. Initially, only a handful of galaxies were detected within its volume. Even later, after deeper searches raised the count to around 60, the Boötes void remained extraordinarily empty. Where many thousands of galaxies would normally be expected, only a few dozen are present in that vast darkness. Discovering such a yawning gap in the cosmos drove home just how unevenly matter is distributed on the grandest scales. For example, when astronomers first identified the Boötes void, they even wondered if there was a mistake or a patch of sky obscured, because hardly any galaxies appeared in that sector of their survey. But the void was very real. Eerie as it sounds, one could imagine drifting alone in the center of the Boötes void. In every direction, you would see almost nothing, maybe a few faint smudges of light from galaxies hundreds of millions of light years away. The usual riot of starlight that fills the sky in our galactic neighborhood would be absent, replaced by an all-encompassing darkness. The silence and solitude of such a place would be profound, a stark reminder of how desolate most of the universe truly is. In fact, even a beam of light would take over 100 million years to journey from the void's center to reach the nearest galaxy cluster at its edge, a staggering illustration of the gulf of emptiness. In the face of such immense emptiness, astronomers began to wonder what effects these voids might have on the cosmos. Could the presence of a truly gigantic void leave a mark that we could detect from Earth? These musings soon converged with a cosmic mystery, a strange cold patch in the faint afterglow of the Big Bang. Some scientists proposed that an enormous void, bigger than any seen before, might be lurking there, casting a subtle shadow on the cosmos itself. In the early 2000s, when astronomers mapped the cosmic microwave background, the faint afterglow of the Big Bang, they discovered something peculiar. Amid the mottled pattern of subtle temperature variations across the sky lay a patch that was significantly colder than its surroundings. This cold spot, as it came to be known, was larger and chillier than what standard cosmology predicted by chance alone. Its existence posed a riddle. What could have caused such a vast, frigid blemish on the otherwise uniform canvas of ancient light? To get a sense of scale, the cold spot spans a region of sky about 5 degrees across, roughly 10 times the diameter of the full moon, in the constellation Eridanus. In absolute terms, it's only a few hundred microdegrees cooler than the average CMB temperature, but statistically, it stood out like a deep dimple on an otherwise smooth surface. Such a sizable cold region was very unlikely to occur at random, according to cosmologists' models. Naturally, this anomaly sparked intense interest and debate. What could create an area of the universe that appears noticeably colder than everywhere else? One intriguing possibility emerged to explain the cold spot. Perhaps a colossal void in the distribution of galaxies lies between us and that remote patch of sky. If an immense region of space were emptier than usual, it could subtly affect the journey of the cosmic microwave background's light. As those ancient photons passed through a huge void, they would lose a tiny bit of energy, emerging on the other side slightly cooler than when they entered. A supersized void could thus imprint a cold spot on the cosmic background, offering a tempting solution to the mystery. It was a bold notion, connecting the influence of a present-day void to light from the dawn of time, and it captured many imaginations. Initially, this was just a hypothesis, with nothing but theory to support it. But it was compelling, because it could be tested with observations. In the mid-2010s, researchers finally gathered data to put this hypothesis to the test, using extensive sky surveys that chart the positions of millions of galaxies. A team homed in on the region around the cold spot. Sure enough, they found hints of an underpopulated expanse about 3 billion light-years away, in the direction of Eridanus. By analysing infrared and optical surveys of that patch of sky, they noticed a deficit of galaxies compared to other regions. It was almost as if a huge section of the cosmic web had been carved out there, leaving a tremendous gap. Estimates suggested that this possible void spanned roughly 1.5 billion light-years in diameter. To put that into perspective, such a scale would make it one of the largest structures ever reported in the universe. Within that immense volume, the density of galaxies appeared to be substantially lower than normal, perhaps by 20% or more. This underdensity might not be a single neat bubble of nothing. It could be a network of smaller voids and sparse regions stitched together. But on the whole, that broad area was far emptier than average, enough that it could plausibly imprint a slight cool spot on the cosmic microwave background. For the scientists who first noted it, this so-called supervoid was an exciting find. Headlines announced the discovery of what might be the largest known structure, linking it to the cold spot mystery. It lent weight to the idea that the cold spot wasn't just a random fluke, but could be a sign of an actual structure influencing cosmic light. If such a void truly exists as described, it would stand as an awe-inspiring example of cosmic scale, an emptiness so vast that it leaves a mark on the oldest light in the universe. The supervoid hypothesis, once speculative, suddenly had tangible evidence behind it, stirring both enthusiasm and further scrutiny. Yet, not everyone was convinced that the case was closed. Subsequent analyses suggested that even a void this large might not fully explain the cold spot's extreme chill. The void, if it exists, probably contributes some cooling effect, but perhaps not enough to account for the entire anomaly. There's also the lingering possibility that the cold spot, strange as it is, could simply be an unusually large random fluctuation in the early universe's temperature map. an improbable coincidence rather than a signature of new phenomena. Meanwhile, a few theorists proposed more exotic explanations. Some speculated that the cold spot might be a bruise from a collision with another universe in a hypothetical multiverse. These ideas, though highly speculative, underscore how exceptional the cold spot appeared to many eyes. So the supervoid hypothesis remains an intriguing, but not yet definitive explanation. To resolve the question, astronomers knew they needed more evidence and a broader search. Was this enormous void in Eridanus unique? Or might there be other huge voids out there subtly shaping what we see? The only way to find out was to keep looking deeper and wider into the cosmic web. Thus began the quest to scour the universe for signs of other great voids and to measure the true influence of emptiness on cosmic observations. Mapping the voids of the universe became a kind of cosmic treasure hunt for astronomers. With the supervoid idea spurring them on, researchers dived into the catalogues of galaxies amassed over decades. Each survey of the sky, each painstaking plot of galaxy after galaxy, was not just about finding what is there, but also pinpointing what is not. By charting the large-scale structure in detail, they hoped to reveal the hidden hollows, the immense cosmic voids that had until recently gone unnoticed. Over the years, technology has provided ever better maps of our universe. Projects like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, allowing scientists to visualize the cosmic web in 3 dimensions. On these maps, voids emerge clearly as vast regions with far fewer galaxies than their surroundings. The galaxies themselves form a glittering lattice on the plot. Each galaxy, a tiny beacon marking where matter congregates, collectively outlining the much larger hollows where matter is scarce. Astronomers can now catalogue voids systematically, measuring their sizes, shapes, and locations, as if assembling a grand atlas of cosmic emptiness. Identifying a void is a bit like noticing a clearing in a forest. One must look for a region where the usual crowd of galaxies thins out dramatically. Statistically, astronomers define voids as areas of space with galaxy densities far below the cosmic average. Sophisticated algorithms comb through galaxy maps, grouping together contiguous zones of underdensity. What they find are cavities of various sizes, often irregular in shape, sometimes roughly spherical, other times elongated, nestled between the filaments of galaxies. And there are many such voids. Modern sky surveys have catalogued hundreds upon hundreds of them, in fact, well over 1,000 in some studies, ranging from relatively modest gaps, tens of millions of light-years wide, to gargantuan chasms, hundreds of millions of light-years across. These voids aren't absolute nothingness. Most contain a few stray galaxies or thin traces of gas. But compared to the cosmic norm, they are astonishingly empty. Each void identified adds to the picture of how matter, and the lack of it, is spread through the cosmos, confirming that emptiness is a defining feature of the universe's architecture. To verify a suspected void's presence, astronomers sometimes turn to the behavior of light for corroboration. One clever approach involves gravitational lensing. Normally, massive clusters bend and focus light, but a large void does the opposite, very slightly widening the path of light passing through it. The result is an anti-lens effect. Distant galaxies seen through a void may appear a bit dimmer or smaller than expected because there's less gravity along the way to magnify them. By carefully measuring the shapes and brightness of galaxies behind suspected voids, researchers can detect this gentle signature of emptiness, strengthening the case that a void truly occupies that line of sight. Indeed, statistical analyses of many voids have detected this weak anti-lensing signal, confirming that these regions are as underdense as they appear. Scientists also study the handful of galaxies that dwell inside voids to glean what life is like in cosmic isolation. These lonely galaxies, drifting far from any crowded cluster, often show traits that set them apart. Many are rich in gas and actively forming stars, suggesting that in the calm of a void, they haven't been disrupted by close encounters with other galaxies. Without the frequent gravitational tussles and stripping of material that occur in dense environments, void galaxies can continue evolving relatively unperturbed. For example, some dwarf galaxies deep in voids have abundant hydrogen gas and bright young stars, whereas similar dwarfs in crowded areas might have lost their gas and ceased star formation. By comparing these isolated galaxies to their cousins in busier regions, astronomers learn how environment shapes the fate of galaxies. As new data pour in from cutting-edge observatories, the hunt for voids presses onward. Upcoming sky surveys and space missions are poised to map the universe in greater detail than ever, likely uncovering countless more voids and sharpening our view of the cosmic web. Telescopes like the recently launched Euclid Space Telescope and the planned Nancy Grace Roman Space Telescope, along with next-generation instruments on Earth, are gathering light from billions of galaxies. These efforts will illuminate the dark gaps between galaxies with unprecedented clarity. Each leap in data brings the enormous patterns of emptiness into better focus, enabling cosmologists to take an ever more precise inventory of voids large and small. For those charting the cosmos, there is a quiet thrill in detecting these vast stretches of nothing. It's akin to standing on a hill at dusk and gazing at valleys where no lights glow. The emptiness itself becomes a profound feature of the landscape. Through patient observation, astronomers have learned that these dark voids are not mere blank spaces, but key chapters in the story of how structure formed. Every void mapped is a testament to cosmic history, a region where matter has flowed away over billions of years, leaving behind a grand silent expanse. By knowing where the voids lie and how large they can become, scientists can now ask a deeper question. What do these enormous empties actually do to the universe? To find out, they must gauge the impact of all this nothingness on cosmic evolution. It turns out that even emptiness has a role to play, subtly influencing the motions of galaxies, the path of light, and the expansion of space itself. Understanding the power of nothing will take us further into the mysteries of the cosmos. In cosmology, even emptiness has consequences. A void may lack matter, but it still influences its surroundings through gravity, or rather, through the absence of gravity. In regions with little matter, there is less gravitational pull to slow the expansion of space. This means that voids effectively expand faster than denser parts of the universe. Over billions of years, the gaps between clusters of galaxies have widened as the voids swell, like ever-growing bubbles pushing galaxies farther apart. It's astonishing to realize that even the near-nothingness of a vast void can shape the fate of cosmic expansion. The effects of emptiness can even be seen in the cosmic microwave background. We saw how a giant void might explain one conspicuous cold spot, but on a broader scale, voids collectively leave a subtle mark on this ancient light. In a universe with dark energy, photons that traverse large voids arrive a bit cooler than they would have otherwise, while photons that pass through massive clusters end up a bit warmer. This is known as the integrated Sachs-Wolf effect, and astronomers have detected it by carefully stacking and analysing the faint signals from many voids and clusters. It's a delicate imprint, but it confirms that dark energy is at work, and that even empty space can slightly alter the temperature of the Big Bang's afterglow. For instance, Directions in the sky where we peer through massive superclusters show up just a bit hotter on the CMB map, whereas directions looking through large voids come out a tad cooler. These subtle signals are a cosmic fingerprint of emptiness and structure. Emptiness also subtly steers the movements of galaxies. While matter-rich regions tug on galaxies and pull them in, an expansive void exerts a kind of push, or at least a relative absence of pull. Galaxies near the edge of a big void tend to drift away from the emptiness and toward denser areas nearby. In effect, a large void creates a gentle nudge, diverting the flows of galaxies outward. In our own cosmic neighborhood, for example, one side of the Milky Way faces a large void that seems to be repelling us, while the opposite side faces the gravitational pull of rich galaxy clusters. Astronomers nicknamed this immense empty patch the dipole repeller because it contributes to our galaxy's motion, effectively pushing us from behind as the Virgo cluster and an even larger concentration of mass called the Great Attractor pull from ahead. In this way, the distribution of voids and masses orchestrates a grand cosmic dance. Together, great emptiness and great mass direct how galaxies and clusters slowly drift over time. Voids have also become valuable tools for probing the universe's fundamental properties, because the growth and size of voids over time depend on the balance of cosmic forces. Measuring voids gives clues about how much dark matter and dark energy exist. So far, surveys show that the number and scale of voids align well with the standard cosmological model, which includes dark energy. In fact, the very presence of such enormous voids is consistent with a universe dominated by dark energy. Without dark energy, gravity would have slowed expansion more, and voids would be smaller. By comparing void statistics with simulations, scientists can tighten constraints on dark energy's properties, using emptiness as a kind of cosmic laboratory. The influence of voids has inspired some radical ideas. A few cosmologists speculated that if we lived inside a truly immense void, it could create the illusion of an accelerating universe without any dark energy. Within such a huge, underdense bubble, local expansion would be faster than the universal average, making distant galaxies appear to recede, driven by a kind of repulsive force. This idea requires that we inhabit a very special place, a void around 1 billion light-years wide, which violates the principle that we occupy no unique spot in the cosmos. While intriguing, this hypothesis remains highly controversial and lacks any solid evidence. Still, it illustrates how cosmic emptiness might skew our perspective of reality. One variant of this concept, called the timescape cosmology, suggests an even subtler effect. In that model, time itself runs at slightly different rates in voids versus dense regions. Gravity is weaker in vast emptiness, so clocks inside a void would tick a bit faster than clocks deep in a massive galaxy cluster. If we happen to reside in an underdense region, our measurements of cosmic expansion could be skewed. What we interpret as acceleration might partly be due to our local perspective. It's a clever twist on general relativity, but it still demands an implausibly large void centered on us. So far, observations show no evidence that such a radical revision is needed. The acceleration appears consistent everywhere, not just from our vantage point. In practice, void observations have tended to bolster the case for dark energy rather than replace it. Studies of voids indicate that while they do expand slightly faster than denser regions, the effect is nowhere near enough to account for the dramatic acceleration seen in supernova data and other cosmological measurements. Instead, what voids provide is another means to measure and confirm the presence of dark energy. For instance, The way voids distort the microwave background and lens distant light agrees with expectations from a dark energy-filled universe. In this way, the voids validate our standard picture. They behave exactly as they should if dark energy permeates space, reinforcing our confidence in this invisible cosmic component. In other words, voids have not upended our understanding at all. Rather, they behave exactly as expected in a universe filled with dark energy, providing yet another piece of evidence for its existence. As time marches on, the role of voids in the cosmic story is destined to grow. Dark energy is accelerating the expansion, causing voids to balloon ever larger. Over the far future, these emptinesses will stretch and merge, isolating galaxy groups from one another. We can envision a distant era where an observer in one galaxy group sees nothing but darkness beyond their local galaxies, the surrounding voids having expanded so much that all other galaxies have slipped out of view. In essence, voids are the expanding spaces that will come to dominate the universe, a preview of the deep isolation that awaits the cosmos in its old age under the reign of dark energy. In that far future, the cosmos will grow ever lonelier. Distant galaxies will slip beyond the horizon, and an observer in one galaxy group will see only darkness where once other galaxies shone, each group marooned in an enormous void of its own making. And yet, for all their influence, voids are not an answer to every cosmic question. There are limits to what emptiness can explain. The supervoid hypothesis, while compelling, has not conclusively solved the puzzle it was meant to address. Many phenomena, like the exact pattern of cosmic background fluctuations or the observed tugs on galaxies, require a combination of factors. Voids alone can't account for everything. Recognizing these limits is important. It keeps us from leaning too heavily on one idea, and reminds us that the universe often demands multiple pieces to complete its puzzle. As we turn to examine the shortcomings of the void theory, we step back and evaluate where emptiness falls short and what mysteries remain beyond its reach. In retrospect, the supervoid hypothesis regarding the cold spot demonstrates both the allure and the pitfalls of cosmic theories. The idea that a single gargantuan void could explain that mysterious cold patch was compelling. Yet, after years of investigation, it remains unproven that the void alone is the full answer. The underdense region detected in the cold spot's direction is real, but it doesn't entirely account for the observed temperature dip. In other words, the supervoid might be part of the story, but not the whole story behind that particular cosmic mystery. Some analyses even suggest the cold spot could simply be a statistical fluke, a rare but not impossible outlier in the random speckle of hot and cold spots from the early universe. In fact, later measurements by the Planck satellite slightly reduced the cold spot's statistical weirdness, hinting it might not be as inexplicable as initially thought. If that's the case, no exotic explanation, void or otherwise, is needed. We may just have stumbled upon one of the universe's chance anomalies. On the other hand, if the cold spot truly demands an explanation, a single void of moderate emptiness may not suffice. Some researchers have found that the cold spot's region contains several smaller voids at different distances, like a stack of empty pockets along our line of sight, whose combined effect could contribute to the cold imprint. Even so, that might only be part of the story, or conceivably, something even stranger is at work. For now, the jury is still out, and the cold spot remains a tantalizing question mark on our cosmic map. The limits of the void explanation become clear here. Cosmic voids, as significant as they are, cannot be invoked to solve every cosmic mystery. The notion that we live in a gigantic void that makes the universe's expansion look accelerated, for example, has been largely discounted. Precise observations show that the acceleration is too uniform across the sky to be explained by a huge local void. Moreover, the void that scenario would require is implausibly vast and finely tuned to our location. Extensive surveys of galaxies around us also fail to find any evidence that we sit inside an enormous void of that scale. In short, voids can't replace dark energy or other new physics wholesale. They are one piece of the puzzle, but not a catch-all answer. There is also a practical limit to what void studies can currently reveal, imposed by the data itself. Finding voids and measuring their subtle effects is challenging because, by definition, there isn't much there. The signals that voids imprint, whether on light from distant galaxies or on the cosmic microwave background, are exceedingly faint, pushing our telescopes and analysis techniques to their limits. Early claims of void effects did stir debate, but over time, improved surveys and methods resolved many of those questions. In general, we find that void influences are real, but also in line with standard cosmology. The whole process underscores how carefully scientists must work to extract answers from the quiet realms of emptiness. All these cautions keep astronomers grounded as they theorize. The void theory, like any scientific idea, thrives under scrutiny. It has yielded valuable insights, shedding light on the large-scale structure, hinting at explanations for oddities like the cold spot, and providing new ways to test cosmic expansion. But it has not upended the fundamentals of our understanding. Instead, the study of voids slots neatly into the existing paradigm, refining our knowledge of the universe rather than overturning it. This is how science advances: bold hypotheses tempered by diligent observations. It reminds us that nature has the final say, and our theories must bow to the evidence the cosmos gives us. In the end, cosmic voids have proven to be both illuminating and humbling. They unveil an architecture of the universe that is both elegant and unexpected. Giant voids framed by filaments of matter, affirming that what we don't see can be just as important as what we do. At the same time, voids remind us that not every anomaly signals new physics. Sometimes a cold spot might just be a statistical hiccup. Emptiness has power, but it also has limits. The exploration of emptiness has still been invaluable. It provided a new test of our cosmological models and reinforced key ideas like dark energy, even if emptiness alone isn't the answer to every riddle. For our journey beyond the visible, the lesson is that each discovery often opens up further questions. Mapping the voids was one step, revealing the vast cosmic lattice and its great gaps. But there are other invisible phenomena we've yet to explore. The universe's hidden tapestry includes not just the voids between galaxies, but other elusive components and forces that shape reality. The story of the invisible cosmos doesn't end here. It only grows more intriguing as we delve deeper. And so, as we leave the realm of cosmic voids, we carry with us the realization that absence itself can speak volumes about the universe. But beyond these voids lies another frontier of the unseen, mysterious influences and entities that pervade the cosmos. In our ongoing quest to illuminate the darkness, we turn next to those unseen forces, continuing our exploration of the endless secrets of the invisible universe. Many mysteries still lurk in that darkness, awaiting discovery. The cosmic symphony of invisible messengers draws our attention not only to distant corners of space, but also to the depths of time. Each whisper from a cosmic ray, each fleeting burst of neutrinos, and each faint ripple of a gravitational wave tells a part of an ancient story. Collectively, they beckon us further back, toward the universe's earliest moments. We follow their lead, journeying to an era when the cosmos was newborn, wrapped in a hot, glowing fog. In that infant cosmos, long before stars or galaxies, subtle imprints were pressed into the fabric of space itself. These imprints, still present after billions of years, hold clues to cosmic events that shaped everything to come. In the darkness of modern space, our eyes cannot see these ancient marks directly. They reside in a form of light beyond the visible spectrum, a gentle afterglow that bathes the entire sky. This is the cosmic microwave background, the faint echo of the Big Bang's brilliance, now cooled and stretched to microwave wavelengths. It surrounds us on all sides, an almost uniform glow only detectable with sensitive instruments. This background light is like a photograph of the universe as a baby, an image taken long before any life existed to witness it. Spread across that image are tiny variations in temperature, slight irregularities that betray places where the young universe was ever so slightly hotter or colder, denser or thinner. Astronomers render this faint background as a map of subtle colours, each hue representing a minuscule difference in temperature from the average. Most of these variations are random speckles, the result of quantum fluctuations blown up by the process of cosmic inflation at the dawn of time. Those tiny fluctuations eventually grew into the galaxies and clusters of galaxies we see around us today. In this way, the mottled pattern on the cosmic microwave background is a blueprint of our universe's large-scale structure. It is a treasure trove of information, a cosmic time capsule carrying messages from when the universe was only a few 100,000 years old. Yet among the gentle, random patchwork of warm and cool spots on this map, one feature stands apart, quietly defying expectations. In a certain patch of sky, far larger and colder than its surroundings, lies a mystery known as the cold spot. While most of the variations in the cosmic background are tiny and statistically unremarkable, the cold spot is different. It covers a region so large and so unusually cold that it caught scientists' attention immediately when the first detailed sky maps were produced. At first glance, it appears as a broad swath of slightly cooler temperature, a faint blue dimple in the cosmic heat map, larger and deeper than any other on the sky. The discovery of the cold spot was met with both excitement and puzzlement. Here was an imprint from the early universe that seemed to whisper of something unexpected. Could it be a statistical fluke, a random chance occurrence in the grand cosmic lottery of fluctuations? Or was it telling us of some special event or structure, either in the early universe or somewhere between those ancient times and our telescopes today? At the time of its detection, no one could say for sure. It became a subject of intense study and debate, a riddle from the dawn of time waiting to be solved. As researchers examined the cold spot more closely, its significance grew harder to dismiss. If the universe were perfectly random in its early fluctuations, the odds of getting such a large, deep, cold region by chance were very small. It was as though the infant universe had left a unique birthmark, one that standard cosmological theories did not readily predict. Some scientists cautioned that even rare events can happen without new physics. After all, given enough area of sky, unlikely things do occasionally occur. Perhaps the cold spot was just a 1 in a million quirk in the cosmic pattern, a statistical outlier with no deeper meaning. But others felt that nature might be hinting at something more profound. To decipher this puzzle, scientists began considering scenarios that could produce such an imprint. The journey of exploration turned speculative and creative. Was there something lurking, unseen, along the line of sight that might have cooled the light from the early universe as it travelled billions of years to reach us? Or did the phenomenon originate at the cosmic dawn itself, an echo of new physics that standard cosmology had yet to account for? Each possibility carried profound implications. With curiosity piqued, researchers looked beyond the usual explanations. They set their sights on the invisible and the exotic, on ideas that stretched the limits of our understanding of the cosmos. In this quest, the cosmic microwave background became more than just a silent image of the past. It became an active playing field for theories. Each subtle anomaly etched in its pattern might be a clue. Perhaps the cold spot was a message from the universe's infancy, left for us to find eons later. If so, what event could have left such an outsized mark? In the smooth fluid of the hot, early universe, what could carve out a region that ended up cooler than its surroundings? It was time to explore answers hidden in the fabric of space and time itself, buried in the realm of the invisible universe beyond ordinary sight. One bold idea was that the cold spot might be the visible imprint of an invisible cosmic relic, a relic not of matter or light, but of a structural twist in the very space that filled the young universe. In other words, some researchers suggested that the cold spot is an ancient cosmic scar left behind by a cosmic texture. In the language of physics, cosmic textures are a type of topological defect, essentially imperfections in the fabric of the young universe. They are akin to knots or twists that form when the universe undergoes rapid phase transitions. Think of how water freezes into ice. As crystal structures form, cracks or bubbles can appear where the freezing isn't perfectly uniform. This is one example of how imperfections can arise naturally during a phase transition. Likewise, as the searing plasma of the early cosmos cooled and transformed, it may have left behind tiny imperfections in the otherwise smooth fabric of space. Cosmic textures represent one possible kind of such imperfection, emerging as the universe's fundamental fields settled into their new states. Not all cosmic imperfections are alike. Theoretical physicists have envisioned other kinds of primordial defects, cosmic strings that stretch like ultra-thin filaments of energy across space, monopolies that resemble isolated magnetic charges, or domain walls acting as invisible boundaries between regions of the young cosmos. A cosmic texture stands apart from these. It has no single, concentrated form or sharp boundary at all. Instead, a texture is diffused over a wide area, a subtle tangle in the fields that permeate space. It is as if the universe tied a knot in itself, a knot without a tight core, one that eventually could slip loose. Crucially, a cosmic texture is not a permanent fixture of the cosmos. It cannot last forever. Over time, the knot in the energy field will eventually start to loosen and unwind, releasing its stored energy back into the fabric of space. When a cosmic texture finally unravels, it is like a coiled spring suddenly letting go, an abrupt but subtle release of tension in space itself. This act of untying has consequences for anything nearby, including the ancient light of the cosmic microwave background. Imagine a background photon wandering through space that happens to pass close to a texture at the very moment it is unwinding. The changing gravitational and energy conditions as the knot releases can give that photon a tiny push or pull, slightly altering its energy. Eons later, when that photon is collected by our telescopes, this effect appears as a faint anomaly in its temperature. In other words, the unwinding of a cosmic texture would leave a telltale sign on the sky, a patch of the cosmic background that is a bit hotter or colder than it would otherwise have been. When cosmologists first mapped the tiny temperature variations of the cosmic microwave background, they wondered if any of those spots could be signals from ancient textures. The cold spot, with its unusual size and depth, immediately stood out as a prime candidate. It wasn't just its rarity that made it intriguing. It was also the particular profile of the cold spot. It has a somewhat rounded, coherent shape and a measurable drop in temperature at its center. Features one might expect if a single event, like the collapse of a cosmic texture, had left its mark. In 2007, a group of researchers analyzed the cold spot and suggested that its properties were consistent with what a cosmic texture's imprint might look like. To them, this enormous cold region might indeed be the lingering evidence of a primordial knot untying itself billions of years ago, an echo of the universe's first moments. If the cold spot were truly caused by a cosmic texture, the implications would be staggering. It would mean that we have, in our sky, direct evidence of physics from a time so early that no star or atom had yet formed, a relic from perhaps a trillionth of a second after the Big Bang. Such a discovery would open a window into the highest energy processes imaginable, offering clues about how the fundamental forces of nature once unified, and then split into the distinct forces we know today. It would connect cosmology with particle physics in a way that nothing else currently can, revealing something about the grand story of how our universe came to be structured the way it is. Beyond the cold spot, the idea of cosmic textures existing at all raises many questions. How many such textures might have formed in the early universe? Are we seeing just one rare survivor, or could there be others lurking as more subtle patterns in the background? Theories allow for the possibility of multiple textures, each eventually unwinding and leaving their own marks. However, each unwinding would be a singular event happening randomly in space and time, so their imprints could be scattered and faint. The cold spot was the first and most obvious candidate. But if it was indeed born of a texture, it was natural to wonder if more evidence could be found by scouring the entire sky for similar anomalies. The cosmic texture hypothesis turned the cold spot from a mere curiosity into a testable prediction. It suggested that the cold spot was not a lone quirk, but part of a family of possible features produced by textures. If one texture had unwound in our observable universe, there might have been others. They might show up as additional unusually large spots, either hot or cold, somewhere in the CMB map. The hunt was on. Scientists now had to comb through the cosmic microwave background data with this idea in mind. Armed with theoretical templates for what a texture signature would look like, they aimed to discover whether the cold spot was unique or just the tip of an iceberg of primordial defects. This was a thrilling prospect. For decades, cosmologists had largely focused on refining our standard model of cosmology, one that includes dark matter, dark energy, inflation, and a nearly uniform early universe with tiny random fluctuations. That model has been extraordinarily successful in explaining observations. But the cold spot, if confirmed as the fingerprint of a cosmic texture, would be a sign of new physics beyond that standard picture. It would show that something extraordinary happened, something not captured in the simplest version of our cosmological story. It was a bold claim, and extraordinary claims require extraordinary evidence. Thus, while the cosmic texture theory for the cold spot was enticing, it had to face the rigorous scrutiny of observation and analysis. With stakes so high, the cosmic texture idea could not remain just an intriguing suggestion. It needed to be tested. The only way to know if this hypothesis held any truth was to confront it with more evidence, Scientists prepared to scrutinize the cosmic microwave background data more closely than ever, armed with the predictions of what textures might look like, if the cold spot were indeed a topological echo from the dawn of time. Then perhaps other subtle texture signatures were hiding in the map, waiting to be discovered. If, on the other hand, no such signs could be found, then the cold spot might stand alone and force a different explanation for its existence. Either way, the quest now moved from speculation to data. It was time to let the evidence speak. The coming analysis would reveal whether the universe had indeed tied and untied knots in its early moments. Cosmic textures, if they exist, would be relics of an early universe event known as symmetry breaking. In the first tiny fraction of a second after the Big Bang, it's believed that the unified forces of nature separated into distinct forces, analogous to how a cooling metal might suddenly become magnetic when its atoms align, or how water freezes and crystals form. If that process of symmetry breaking wasn't perfectly uniform everywhere, it could have left behind defects in the energy field filling space. Most cosmological models, like the inflation theory, assume such defects either never formed in significant numbers or were stretched away. That's why detecting a texture today would be so extraordinary. It would challenge some assumptions and shine a light on physics at energies far beyond what we can achieve on Earth. The data analysis that followed turned into a quiet yet profound adventure in cosmology. Having a compelling hypothesis is one thing, but science demands proof. If a cosmic texture had indeed left its fingerprint on the sky, researchers needed to unearth more evidence for it. The cold spot by itself was suggestive, but one lone anomaly could always be a coincidence. The challenge set before the cosmologists was clear. Search the entire cosmic microwave background map for any additional signs that might confirm the presence of cosmic textures. It was a bit like sifting through sand for a few hidden, precious gems, where the gems were subtle patterns hidden in a vast sea of cosmic noise. Teams of scientists got to work, armed with data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, satellite, which had mapped the microwave sky with unprecedented precision. The task was to scan this map for telltale texture imprints. But what exactly were they looking for? A cosmic texture's signature would likely appear as a circular or nearly circular spot, either slightly cooler or slightly warmer than the surroundings, with a particular profile, a gentle change in temperature from the center of the spot to its edges. The cold spot itself fits this description fairly well, but to truly test the theory, they needed to see if other, perhaps smaller or less obvious, spots of this kind were scattered elsewhere on the sky. This was easier said than done. Imagine examining a world map covered in random ink splatters, trying to find perfect circles. The human eye can play tricks, seeing patterns where none truly exist. A blotch or a blur might look like a circle one moment, and like nothing in particular the next. To avoid fooling themselves, the researchers relied on algorithms, mathematical pattern finders that could systematically comb through the data without bias. They programmed computers to simulate the cosmic microwave background many times over, generating fake skies based on the standard cosmological model without any textures. By comparing these simulations with the actual sky map, the algorithms could pick out anomalies that stood out above the random noise. One approach was to essentially slide a filter across the sky, a template of a round spot in various sizes that could match what a texture imprint would look like. At each position on the map, and at each scale, they asked, "Does the sky here resemble the kind of spot a texture would produce?" It was an enormous search, considering all possible locations and sizes of spots, and it pushed the limits of computational power available at the time. Each potential hit Each place that vaguely looked like a texture's footprint had to be assessed for how likely it was to appear by chance. The vast majority of potential spots that turned up in this automated search were not particularly significant. They were about as common as one would expect from random fluctuations. Still, among all those billions of pixels of data, the cold spot remained the most conspicuous oddball. In the initial pass with WMAP data, no other feature quite like it jumped out. Scientists found that aside from the cold spot, the microwave sky was generally consistent with the random speckles predicted by the standard model of cosmology. If textures had been abundant in the early universe, the analysis should have uncovered not just one, but many unusual spots. The absence of a crowd of such features was telling. In statistical terms, it allowed cosmologists to set an upper limit on how many textures could be out there. The results indicated that textures, if they exist at all, must be exceedingly rare. By 2012, the first thorough, full-sky search for cosmic textures was completed, and the findings were sobering. Aside from the cold spot itself, there was no clear evidence of any other texture-like signatures in the WMAP data. The researchers reported that their analysis could rule out any theoretical model that predicted a large number of textures. In technical terms, if a theory suggested that a dozen textures should have formed across the sky, that theory now looked very unlikely. The data simply did not show that many unusual spots. Their report placed a confidence limit, saying in effect, "We can be 95% sure that there aren't more than a handful of texture imprints in our observable universe." In everyday terms, that meant if the cold spot was indeed caused by a cosmic texture, it might well be one of the only ones of its kind, a cosmic rarity. For those who had hoped the cold spot would be just one piece of a larger pattern, this result was a clear reality check. This outcome was both a relief and a disappointment, depending on whom you asked. On one hand, the standard cosmological model, the one without exotic textures, had weathered the challenge. The absence of multiple texture signals meant that the simple, elegant picture of the early universe, seeded by random fluctuations and stretched out by inflation, was still holding strong. There was no immediate need to rewrite the cosmology textbooks. On the other hand, the mystery of the cold spot persisted. If it was unique, then understanding it might require a unique explanation. The texture hypothesis was not entirely ruled out, but it no longer had the support of a pattern of similar spots elsewhere. It was as if nature had left just one enigmatic clue, and no others to back it up. Scientists did not stop with WMAP. The Planck satellite, launched by the European Space Agency, took the quest a step further a couple of years later. Planck measured the cosmic microwave background with even higher resolution and sensitivity, providing an even sharper view of the sky. If any small texture-like features had been hiding just below WMAP's detection threshold, Planck was designed to sniff them out. When Planck's full sky maps were released, cosmologists eagerly repeated the texture search on this pristine new data. The cold spot was still there, a confirmed feature, not an artifact of measurement, but the story for textures remained unchanged. Planck, like WMAP, did not reveal a troop of lesser cold spots or hot spots that would scream textures from the early universe. The cold spot stood alone in its strangeness. This painstaking scrutiny of the sky did have a silver lining. By not finding abundant evidence of textures, scientists managed to place new constraints on theories of the early universe. Some exotic ideas about how the universe's earliest phase transitions occurred were now less plausible, as they would have generated more textures than we see. Conversely, if there is a theory that yields perhaps just one texture in the observable universe, the cold spot might fit comfortably into that narrative. But such a theory would require a strange fine-tuning of fate, making our patch of the universe special in a way that cosmologists usually resist accepting without strong evidence. After years of searching, the conclusion was tantalizingly inconclusive. The cold spot could be a texture, but if so, it's a lone one in our sky, making it a very improbable event under most models. Alternatively, it could be that the cold spot is not a texture at all, and something else entirely is responsible, something that doesn't produce multiple clones of itself across the heavens. In science, ruling out possibilities is as important as confirming them. The searches with WMAP and Planck effectively ruled out a whole class of theories that predicted numerous texture imprints. What remained was either the possibility of a one-off texture arising from highly unusual initial conditions, or the need for a different explanation altogether. Through this meticulous testing of the texture hypothesis, one thing became clear. The cold spot was not going to give up its secrets easily. The initial excitement of the cosmic texture idea had met the hard scrutiny of data, and the universe replied with a bemused silence. No chorus of texture signals echoed across the sky. Only that single, solitary note, the cold spot itself, lingering mysteriously. If it was truly an echo from the dawn of time, it was a lonely one. And if it was not, then the cosmic microwave background was teasing us with a chance coincidence, or pointing to some other new physics not yet understood. In the aftermath of these searches, cosmologists found themselves both wiser and more perplexed. They had learned how to push their data analysis techniques to new limits, how to carefully distinguish real features from imagined ones, and how to extract meaningful constraints on theoretical ideas. Yet, the fundamental question remained unanswered. What is the cold spot telling us? The texture test had come back negative for the most part, but the test itself taught valuable lessons. It showed that our universe, in its vast expanse, mostly behaves as expected. Mostly, but not entirely. It is that small deviation from the ordinary, that stubborn cold spot, that continues to intrigue and trouble the minds of scientists. If the cold spot wasn't accompanied by an army of other textures, then perhaps the key to its existence lay elsewhere. Scientists began to consider other possibilities with renewed interest. Maybe the anomaly wasn't born in the ultra-early universe after all. Perhaps something closer to home, in cosmic terms, could be the cause. Or maybe there were entirely different new physics at play, ones that would not leave multiple imprints, but could still produce one grand cosmic oddity. In grappling with the negative result of the texture search, researchers effectively cleared the ground of one hypothesis. This made room for them to explore other ideas with greater attention. The journey was far from over. The cold spot remained, as ever, an invitation to further discovery, urging us to look deeper and think harder about the universe's hidden corners. The cold spot is not the only puzzle hiding in the cosmic microwave background. As scientists delved deeper into the data, they found that our universe's baby picture contained a few other irregularities. Subtle fingerprints that did not quite fit the pristine random pattern predicted by theory. These strange features became additional clues, hinting that something might be amiss or incomplete in our understanding. Each anomaly by itself is small, and none shout as loudly as the cold spot. But together, they form a chorus of whispers, suggesting that the universe may have a few secrets left in its earliest chapters. One of these curious features has been nicknamed the axis of evil, a dramatic moniker for a subtle oddity. When cosmologists analysed the largest scales of the microwave background map, they expected the hot and cold spots to be oriented randomly, with no particular direction preferred over another. The universe, after all, has no up or down, no special axis. At least, it shouldn't. But to their surprise, The biggest fluctuations in the CMB, patterns spanning huge swaths of the sky, seem to have a strange alignment. Imagine looking at the ripples on a pond and noticing that the biggest ripples all line up in one direction, as if pointing toward the same compass point. That's roughly what the axis of evil refers to. The observed alignment of the cosmic microwave background's largest temperature variations along a certain axis across the sky. This axis runs through the celestial sphere in a way that intriguingly lines up with the plane of our solar system, which made some scientists initially suspect a measurement artifact. Perhaps some leftover glow from the solar system or our galaxy was contaminating the data, skewing the patterns. Yet, even after careful cleaning of the data, the alignment persisted, leaving cosmologists scratching their heads. It was an uncomfortable result. In this context, evil was not meant literally. It signified that the finding threatened a cherished cosmic principle, isotropy, the idea that the universe looks the same in all directions. If the alignment were real and not a fluke, it might imply that there's something about the geometry or initial conditions of the universe that sets a preferred direction. Such a notion borders on the heretical in standard cosmology. Another odd hint comes from a simple question. Does one half of the sky look like the other half? For a nearly uniform universe, the answer should be yes. Take any way you split the sky, the total variations in the CMB on one side should statistically mirror those on the other. Yet researchers noticed a slight imbalance. One hemisphere of the sky, defined in a particular way, shows marginally stronger fluctuations than the opposite hemisphere. It's as though the cosmos has a faint, two-faced quality. A northern side and a southern side that aren't perfectly alike. This is called the hemispherical power asymmetry. The difference is small, and it's tricky to measure. Still, it appears to be there in the data, nudging us to wonder if the cosmic principle of no preferred direction might have its exceptions. Could it be that our observable universe, by sheer accident, happened to have a bit more primordial lumpiness on one side? Or is there physics at play that made one half of the newborn universe ever so slightly different from the other? Then there's the mystery of the low power on large scales. When scientists look at the CMB, they analyze it in terms of patterns of different sizes. The theory of inflation, our best explanation for the early universe's rapid expansion, predicts how strong the fluctuations should be on various scales. By and large, it's spot on. But at the very largest scales, patterns that span the entire sky, the observed fluctuations are weaker than expected. In particular, the so-called quadrupole, a pattern that divides the sky into 4 alternating patches of high and low temperature, is unusually faint. It's as if the broadest brushstrokes of the universe's baby picture were painted a little too lightly. By itself, this large-scale quirk could be shrugged off as a statistical fluke. But taken together with the other curiosities, it adds to an uneasy feeling that the cosmos is just a bit stranger than expected. Some wonder if these anomalies, collectively, hint at new physics, while others suspect we may simply be encountering the inevitable oddities that random chance produces. Either way, the coincidence of multiple anomalies keeps the questions alive. Scientists have approached these anomalies with cautious fascination. Each could be nothing more than random chance. After all, in any random pattern, some lines will appear to align by coincidence, and some areas will look a bit different than others. There's a risk of overinterpreting noise, of seeing faces in the clouds. And indeed, a majority of cosmologists lean toward the view that most of these large-scale anomalies, tantalizing though they are, may well be statistical flukes or the result of unaccounted systematic errors. But not everyone is content with that shrug. The fact that multiple independent oddities exist in the same data set gives pause. It's like walking into an old house and finding a door slightly ajar, a window unlatched, and a book fallen off a shelf. Any one of those could be a coincidence, but together, you start wondering if something more is going on. For the cold spot especially, alternative explanations have garnered significant attention. If it isn't a cosmic texture, what else could have made this region of the sky cooler than expected? One down-to-earth possibility is that the cold spot isn't telling us about the dawn of time at all, but rather about a structure much closer to us. In 2007, a group of astronomers proposed that a colossal supervoid, an enormous region of space with far fewer galaxies than average, lies between us and the cold spot area of the CMB. If true, this great void would be billions of light years across, making it by far the largest known void in the universe. How could such emptiness make the cosmic microwave background appear colder? The answer lies in the subtle dance of light and gravity. As cosmic microwave background photons journey toward us, they sometimes pass through large clusters of galaxies, or, conversely, through vast, empty voids. When a photon falls into the gravitational well of a massive cluster, it gains a bit of energy, getting blue-shifted, and as it climbs back out, it loses that energy, ending up roughly where it started. In an expanding universe, however, this balance can tip. If the universe is accelerating due to dark energy, a photon climbing out of a gravitational well late in time doesn't quite lose all the energy it gained falling in, because the well itself has stretched and shallowed by the time it leaves. Conversely, if a photon traverses a great void, it loses energy going in and gains some back coming out. However, if the void's depth diminishes during the photon's transit, the photon doesn't regain everything it lost. The net result is that the photon emerges a bit less energetic, in other words, cooler, than it would have been otherwise. This phenomenon is a version of the integrated Sachs-Wolf effect, a way that evolving cosmic structures imprint on the CMB. If a supervoid of extraordinary size sits in front of the cold spot area, it could potentially account for part of the temperature dip we see. Surveys of galaxies have indeed hinted at something unusual in that direction of the sky. Radio telescope maps once noted a decrease in the density of distant radio sources toward the cold spot, and later, other studies using infrared and optical surveys reported evidence of a vast, underdense region. Astronomers sometimes call it the Eridanus supervoid, named after the constellation in which the cold spot lies. One study in the mid-2010s claimed to find a void roughly 1.8 billion light-years across, centered a few billion light-years away from us, lining up with the cold spot's position. If this is real, it's a stunning structure in its own right, a cosmic cavern nearly empty of the usual galaxies and matter. Such a void would rank among the largest cosmic structures ever identified. However, even a void of that magnitude might not fully explain the cold spot's chill. Detailed calculations bear this out. They indicate that while a giant void would indeed make that patch of the CMB a bit colder, it likely falls short of accounting for the full observed dip in temperature. In other words, a supervoid might be part of the story, but not the whole story. Additionally, the very existence of such a gargantuan void is contentious. Our universe's structure formation models allow voids, but a void that large is at the extreme tail of probability, much like the cold spot itself. Some galaxy surveys have questioned whether the apparent supervoid is truly as empty as initially reported, or whether the statistical significance of the void's detection is robust. Like the cold spot, the void claim stands out and invites skepticism and further verification. Or perhaps these anomalies are hints of something fundamentally new, like a non-trivial cosmic topology or an imprint from before inflation. As it stands, the alignments and asymmetries remain unresolved curiosities. They could still turn out to be mere statistical flukes, or they might point to physics beyond our current understanding. For now, they keep scientists wondering and questioning their assumptions. On the more exotic end of possibilities lies a hypothesis that sounds like science fiction: the cold spot as a bruise from another universe. In the framework of cosmic inflation, it's conceivable that our universe is just one bubble among a potentially vast multiverse of other bubble universes. If two bubbles collided early in their expansion, they might disturb each other's contents. Picture two soap bubbles drifting and gently bumping. They might create a circular patch or distortion where they touched. Some theorists have speculated that such a collision could leave a circular blemish on the cosmic microwave background, perhaps a region of slightly lower temperature. The cold spot's roughly circular, isolated nature made it a tempting target for this idea. Could it be the aftermath of our young universe colliding with another bubble universe long ago, imprinting a cool region in the radiation we observe today? This multiverse collision scenario is highly speculative, but it fired imaginations. Remarkably, it was an idea that could be tested by physicists, at least in principle. Cosmologists developed algorithms to hunt for disk-like patterns in the CMB data that might indicate collisions between universes. They scanned WMAP and later Planck maps for telltale signatures of such cosmic bruises. What they found was, again, not a smoking gun, but a few intriguing candidates. And one of them was indeed the cold spot. The cold spot showed up in these searches as one of the largest and most significant circular anomalies. However, the evidence was not strong enough to declare a detection of a bubble collision. The odds that such a pattern could arise by chance were not low enough to rule out a fluke definitively. So while the cold spot did nothing to disprove the multiverse idea, it didn't confirm it either. The multiverse explanation remains a fascinating, if unprovable, possibility. Faced with these various clues, alignments, asymmetries, voids, and even whispers of other universes, cosmologists have been both humbled and inspired. Humbled because the universe has once again reminded us that it may not conform perfectly to our neatest models. Inspired because every anomaly is an opportunity to discover something new. Each anomaly rekindles the drive to probe further and understand the cosmos more deeply. Each proposed explanation for the cold spot or related anomalies, whether prosaic or profound, spurs new research. Astronomers design sharper surveys to map galaxies and find voids or confirm their absence. Physicists refine their models of inflation to see if a small tweak could produce an outsized cold region or an alignment of patterns. Some have wondered if a non-standard period in the early universe, say an exotic physics phase transition or a subtle energy field, might cause not one but a set of anomalies, tying them together under one theoretical umbrella. In essence, the anomalies have kept the field on its toes. As of now, none of the alternative theories for the cold spot or the other CMB curiosities has emerged as a clear winner. The void explanation has its merits, but doesn't seem to entirely solve the puzzle. The texture theory, as we explored, is heavily constrained, and alone doesn't look likely unless we're extraordinarily lucky to have just one in view. The chance alignment or statistical fluke interpretation is still very much on the table, unsatisfying to some, but a real possibility given the large cosmic canvas we're drawing from. The multiverse collision idea, while captivating, may forever lie in the realm of the untestable, unless some other observable imprint of another universe is found. and the axial alignment and hemispheric differences remain unresolved curiosities. Perhaps trivial after all, or perhaps hints of something fundamentally new. What these clues have done is keep the dialogue open. They remind us that even in an era often dubbed the precision cosmology age, where we've measured cosmic parameters to high accuracy, there are still mysteries lurking at the edges of our maps. The cosmic microwave background, for all its wealth of information, still has a few smudges and oddities that make scientists furrow their brows and ponder. With each new dataset, they eagerly check. Is the cold spot still there? Yes, it always is. Has it changed? No, it remains as it was, a fixed feature of our sky. Do the anomalies persist in new observations? Yes, Planck saw the same odd alignments and asymmetries as WMAP, confirming they are not mere artifacts of one satellite. Perhaps the next breakthroughs will come from new kinds of observations. Future missions might measure the polarization of the CMB even more precisely, potentially unveiling subtle traces of whatever caused the cold spot, though there is no guarantee. Large-scale surveys of galaxies and cosmic structures, ever-growing in scope, could either discover more megavoids, strengthening the void case, or show that our neighborhood isn't so special after all. Or maybe a completely different cosmic messenger, say primordial gravitational waves or the cosmic neutrino background, could one day reveal clues about unusual events in the early universe that left imprints like the cold spot. These ideas are speculative threads, but science often progresses by tugging on such threads to see what unravels. In this way, the cold spot has evolved from a peculiar blotch on a map into a central character in cosmology's ongoing story. It is a challenge thrown down by the cosmos. Explain this, if you can. Alongside its fellow anomalies, it keeps cosmologists from resting easy, ensuring that we continue to test the limits of our theories and the reach of our observations. Each clue in the CMB is a reminder that the book of the universe is not yet fully written. There are footnotes and enigmatic passages that require further interpretation. And as long as those mysteries endure, scientists will continue the quest, driven by the hope that even the strangest cosmic cold spot can ultimately be illuminated by human curiosity and ingenuity. The scene opens on a vast, silent darkness speckled with distant stars. We drift away from familiar galaxies and nebulae, moving farther out, as if at the edge of everything we know. In this tranquil cosmic stillness, a profound thought emerges. What if our universe is not the only one? What if beyond the farthest star we can see, beyond even the invisible reach of our telescopes, lie countless other universes, floating in an endless expanse? The mind stretches to imagine it, an infinite tapestry of realities, each a world unto itself. In this gentle exploration, we begin to see our own universe as just one tiny bubble in a vast cosmic ocean, one among many. Our journey shifts perspective, envisioning the cosmos from far outside our known boundaries. From this vantage point, the Milky Way is just a faint glimmer, and our observable universe a mere speck. We allow ourselves to wonder at the possibility that surrounding this speck are other specks, other bubbles of space and time, as real as our own. This is the multiverse perspective, an idea that whispers that creation may be far grander than we ever imagined. The notion of a multiverse once seemed like pure speculation, a fanciful tale reserved for science fiction or wild imagination. But slowly, through the lens of modern physics, it has tiptoed into the realm of serious thought. It beckons us to step beyond the comfort of the known and contemplate a reality where the word universe no longer means everything, but instead becomes just one chapter in an endless story. The multiverse idea wears many faces. Some envision it as an ever-branching tree of possibilities, where every decision and every quantum event spins off a new world in a parallel dimension. Others picture it as a grand cosmic quilt stitched together by the fabric of string theory, each patch a universe with its own laws. In our current journey, we follow a particular thread of this tapestry, the one woven by the physics of cosmic inflation. This theory, widely embraced to explain the uniform glow of our cosmic microwave background and the large-scale structure of galaxies, hints at something astonishing when taken to its limits. In the first fleeting fraction of a second after the Big Bang, space itself is thought to have ballooned outward at a stupendous rate, doubling in size over and over, far faster than the speed of light. This burst of expansion was not gentle or uniform. It may have been chaotic and eternal, creating not just our bubble of space, but innumerable others beyond our reach. We imagine that initial moment of inflation as a kind of boiling of space-time, where one tiny bubble of vacuum energy swells into our universe. Countless other bubbles continue to inflate elsewhere, sprouting like foam on the crest of an endless ocean wave. Each bubble becomes a universe, expanding and cooling, with galaxies and stars eventually taking shape within, much like our own. Yet each bubble remains isolated, separated from its siblings by regions of still expanding space that push them ever farther apart. The speed of light imposes a strict limit that none of us can break, and so these bubble universes cannot exchange a single photon or particle once they drift apart. They are truly separate realms, each sealed off by the relentless expansion of the space between them. For all practical purposes, each bubble universe is oblivious to all others, like a lone island in a vast cosmic sea. As we drift in this thought experiment, we come to see our universe in a new light, not as the all-encompassing reality, but as a single drop in a vast cosmic sea. Within our drop, all of human history and every star we've ever seen are contained. But beyond the shimmering surface of our cosmic drop, other drops sparkle in the darkness, containing their own wonders. It is a humbling and exhilarating perspective. For generations, humanity's eyes have gazed out and seen darkness at the edge of the observable skies, assuming that beyond lies simply more darkness, or perhaps nothing at all. Now, the multiverse perspective invites us to think bigger. Beyond the edge of the observable horizon, perhaps creation did not cease. Perhaps it goes on endlessly, hosting realms we have yet to dream of. This perspective does not come without questions or doubts. How could we ever know if these other universes truly exist? If they are forever out of reach, does it even count as science to speak of them? These are fair questions, and scientists themselves debate them earnestly. Yet, tantalizing hints in our theories keep this multiverse hypothesis alive. In the strange mathematics of quantum mechanics, every possibility can be seen as real, somewhere in some branch of reality. In the elegant equations of string theory, there are landscapes of possible universes with different properties. And in the logic of inflationary cosmology, once inflation begins, it curiously may not end everywhere at once. It stops in patches, our patch being one, and elsewhere it continues, creating more patches without end. It is as if we lit a fire of creation that cannot be fully extinguished. It pops and crackles beyond our sight, igniting new universes, even as ours cools and ages. So here we stand, metaphorically, on the shoreline of the only cosmos we know, peering out at a vast, unknown ocean. The waves of that ocean are hidden in darkness, beyond any telescope's gaze. We cannot sail there. We cannot communicate across the gulf. Yet the mind's eye sees the faint glimmers of distant possibilities. It's a quiet, awe-inspiring vista. For a moment, imagine being able to float above this cosmic ocean, seeing bubble upon bubble dotting the expanse. Each may have its own story. Perhaps some grew hot and dense like ours, and gave birth to galaxies and life, while others took different paths, governed by different cosmic rules. Perhaps some bubbles fizzled out, never forming stars, while others shone with brilliance beyond anything in our own universe. In the stillness of this thought, one question begins to surface gently. If these countless other universes are out there, have any of them ever touched ours? The bubbles of space-time are mostly isolated. But what if, in the distant past, two bubbles drifted close? Could they collide or gently brush against each other? And if so, what would that mean for the inhabitants of those universes? Would there be a momentary window where the barrier between realities thinned? As we ponder this, the idea transforms from a philosophical musing to a cosmic detective story. Perhaps, if two universes had ever interacted, there might be subtle clues left behind. We might not be able to travel beyond our universe's edge, but maybe the universe itself bears scars or memories of a past encounter. And thus we are drawn to consider one of the most startling possibilities the multiverse concept offers. Evidence that our universe has experienced a collision with another. The thought of universe colliding with universe is both startling and strangely logical when we think of them as bubbles in a larger space. In the physical world, we know no bubble bath is without a few bubbles bumping into each other. Why would the multiverse ocean be any different? Granted, these are not soap bubbles but entire cosmic expansions, so the mind reels at the scale. Two universes meeting would be an event of almost inconceivable energy and consequence. If it occurred, especially in the early formative years of a universe, it could send a ripple or shockwave across the fabric of space-time. For those inside our universe bubble, it might be perceived only indirectly, perhaps through a faint imprint in the sky. So we ask, if such a cosmic collision ever happened long ago, could we find a mark, a bruise, an echo of it as we gaze into the heavens today? With our curiosity kindled and our perspective widened, we gently turn our attention to the subtle clues that might lie hidden in the oldest light of our universe. High above us, the sky holds a faint afterglow of the Big Bang, a soft whisper of light that has travelled for nearly the entire age of the universe. This is the cosmic microwave background, the CMB, a nearly uniform glow that fills the cosmos and comes to us from all directions. It is as though we are immersed in a pale relic light, the remnant of the time when the first atoms formed and the universe became transparent. The CMB is remarkably smooth, like a warm blanket, with only tiny, subtle variations in temperature from point to point. Those variations, just a few millionths of a degree hotter or colder, are the imprint of primordial sound waves and fluctuations when the universe was newborn. They are the seeds from which galaxies eventually grew. To the naked eye, or even to a sensitive telescope, the CMB would appear almost featureless. But when measured with exquisite precision, it reveals a mottled pattern, tiny speckles of slightly different temperatures scattered across the sky, almost like a delicate cosmic wallpaper. Amid this delicate pattern, one particular feature has captured the attention and curiosity of cosmologists worldwide. It is known simply as the cold spot. In a map of the cosmic microwave background's faint ripples, the cold spot stands out as a region a bit cooler than its surroundings. That might not sound extraordinary at first. After all, the CMB has many warm and cool spots at smaller scales. But the cold spot is different. It spans a patch of sky roughly 5 degrees across. To put that in perspective, that's about 10 times the width of the full moon in the sky, an enormous region by cosmic standards. And within this wide patch, the temperature is slightly lower than average by a tiny fraction, only a few 100,000ths of a degree. In scientific terms, it's colder by about 1 part in 18,000 compared to the rest of the CMB. That difference is minuscule on an everyday thermometer. But for something as smooth as the CMB, it's an anomaly. It's as if we found a spot on a perfect billiard ball that, upon the closest inspection, dips just a little more than expected. Notable not because it's huge, but because it's unexpectedly large, given how smooth the whole surface usually is. The discovery of the cold spot emerged in the data from satellites that mapped the CMB, first with NASA's Wilkinson Microwave Anisotropy Probe in the 2000s, and later confirmed by the European Planck Observatory with even higher precision. Scientists at first approached it cautiously. In the early days, some wondered if it was just a statistical fluke, a random blob in the noise of the data that only appeared significant by chance. After all, when one looks at random patterns long enough, occasionally an oddball feature can pop out just by luck. And indeed, calculations suggested that while unlikely, such a large cold region could occur naturally in the standard cosmological model, perhaps 1 or 2 times out of 100. In other words, there might be a 1 or 2% chance that the cold spot is simply a rare but perfectly natural occurrence in an otherwise ordinary universe. If that were the case, then eventually we'd just accept it as a quirky but meaningless coincidence. For some time, this remained a plausible stance, that the cold spot might truly be just a statistical fluke with no deeper significance. Yet the cold spot's mystery invited deeper investigation. If it wasn't just a fluke, what could cause such a broad, cool region in the CMB? One of the first serious ideas was linked to an intervening structure, a vast void in the distribution of galaxies between us and that part of the sky. Picture a region of space hundreds of millions of light years across, containing far fewer galaxies than average, essentially a tremendous cosmic cavity. If the CMB's light travelled through such an underdense region on its way to us, it would have been affected by what's known as the integrated Sachs-Wolf effect. In simple terms, as light moves through a large void, the stretching of space due to dark energy can cause the light to lose a bit of energy. Think of it as a traveller climbing out of a valley. If the valley is shallow, they lose little energy, but if it's a deep valley, the effort is greater. A photon crossing a big void might emerge slightly less energetic, which in the context of the CMB means cooler in temperature. So, a supervoid, an immense region with much less matter, along the line of sight, could imprint a cold spot on the CMB. For a time, this idea of a supervoid aligned intriguingly with observations. Some surveys of galaxies hinted at just such an underpopulated region in the direction of the cold spot, roughly billions of light years away. It was as if we found a cosmic cavern in that part of the universe, sparsely populated by galaxies and clusters. Hopes rose that this could be the explanation, an impressive but not entirely exotic phenomenon, a hole in the large-scale structure of the universe casting a cool shadow on the ancient light. However, as more data rolled in, the picture became less clear. Astronomers mapped galaxies and measured gravitational lensing in that patch of sky, to gauge just how empty that region truly was. Their findings suggested that while there is indeed a void-like region, it isn't quite void enough. The detected lack of galaxies, though notable, would only account for a portion of the cold spot's temperature drop, not the whole thing. It was like finding a shallow dent where we expected a deep crater. With the supervoid explanation weakening, the puzzle of the cold spot deepened. Scientists were left with an anomaly not easily explained by conventional cosmology. That is when some began to entertain a more exotic possibility. If known physics couldn't easily account for this cold patch, perhaps something fundamentally different was at play. And here the multiverse perspective quietly stepped back into the conversation. A few researchers proposed a bold scenario. What if the cold spot is the mark of an ancient encounter between our universe and another? In their vision, during the very early moments of cosmic inflation, our expanding bubble universe might have brushed against another bubble universe nearby. The two universes, each a realm of space and time in its own right, could have collided or at least interacted for a brief moment before pulling apart. That interaction, like two soap bubbles bumping into each other, might have left a disturbance, a bruising, in the fabric of our young universe. If such a collision did occur, it could have sent a ripple across the fabric of our infant universe. The physics of it is hard to fathom, but one likely outcome is clear. The encounter would leave a round imprint on the young cosmos. The collision might have disturbed the hot primordial plasma in a vast circular region, subtly altering its temperature there. Billions of years later, that disturbance would appear in the cosmic microwave background as an unusual patch. The cold spot, broad, circular, and cooler than its surroundings, fits this expectation surprisingly well, so much so that it earned the nickname Cosmic Bruise. It sounds like science fiction, yet this hypothesis has been seriously proposed by scientists who grapple with data that defies easier explanation. The cosmic bruise idea captured imaginations. For the first time, a piece of data, that pale blue spot in the all-sky map of the CMB, offered a possible hint, however tentative, that we might not be alone in the grandest sense. Think of it, a silent message in the sky, potentially written by a neighboring universe long ago, telling us that I was here, I bumped into you. It's a mind-boggling interpretation. Many in the scientific community greeted it with healthy skepticism, as extraordinary claims demand extraordinary evidence. No one was ready to conclude we had proof of a parallel universe. But the mere possibility turned the cold spot from a curious glitch into one of the most scrutinized patches of sky. If our universe has bruises, what a story that tells about its past. Still, a bruise alone is not confirmation. It is a clue, one that demands we search further and examine it from every angle. So the question becomes, how would we know for sure? What other evidence, what other signatures would a cosmic collision leave in its wake? With curiosity and caution, scientists set out to search systematically for these signatures of a collision, to see if the cold spot is unique or one of many, and to test whether our universe really bears the scars of a past cosmic encounter. The scientific hunt for evidence of a cosmic collision unfolds like a grand detective story, armed with the hypothesis that another universe may have left its mark on our own. Cosmologists turned to the one place such a sign might be preserved: the cosmic microwave background. If a neighboring bubble had crashed into ours in the distant past, then amid the random speckles of the CMB's heat map, there could be a subtle pattern left behind by that cataclysmic meeting. Already, one suspicious clue, the cold spot, had captured attention. But to prove it was truly a bruise from a bubble collision, Scientists needed more than an intriguing anomaly. They needed a systematic search for definitive signatures, telltale fingerprints of a cosmic fender bender, and a way to distinguish them from the noise of an ordinary universe. Extraordinary claims would require extraordinary evidence, and that evidence would have to come from a careful, systematic analysis of the cosmos. Researchers began by asking, what exactly would a bubble collision imprint look like in the CMB? From theoretical simulations and calculations, a clear prediction emerged. The collision would produce a circular region, like a pale disk on the sky, with a distinctive temperature profile. Perhaps it would be slightly cooler in the center and warmer at the edges, or vice versa, depending on the details of the physics. But it would stand out as an unusually symmetric, round patch, larger than typical fluctuations. In a sky full of random blotches, such a collision scar would resemble a single perfect ripple in a choppy sea, subtle but discernible with careful analysis. The challenge was immense. The CMB data is essentially a giant spherical image, with tiny temperature deviations at millions of points. Within this vast sea of data, a collision signature could, in theory, appear anywhere and at any size. It would be as if one were looking for a faint watermark on an ocean's surface, not knowing where on the globe it might be. Early attempts to eyeball the data weren't enough. Human vision is too easily fooled by randomness, seeing patterns where none exist. So a team of cosmologists developed sophisticated algorithms to automate the search. They created simulations of what a bubble collision would look like superimposed on a CMB sky, and then trained their software to detect those patterns. By statistically filtering the data, the algorithm could flag regions that had the circular, disk-like characteristics of a potential collision, while estimating the likelihood that such a region could arise by chance alone. In essence, they taught computers to find the subtle clues that the human eye might miss. This first systematic search for cosmic collision signatures was carried out on maps from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, one of the satellites that had measured the CMB with great precision. The result of the search was intriguing. The program identified a handful of candidate spots, regions that might just be scars from ancient collisions. Among them, unsurprisingly, was the already notorious cold spot. But there were a few others scattered across the sky that also showed up as somewhat anomalous circles. Had we found proof of the multiverse? The scientists involved were cautious and quick to temper excitement. It's all too easy, they reminded everyone, to find faces in the clouds, patterns that entice our imagination but are ultimately coincidental. They rigorously checked how often purely random CMB maps would produce similar circular features. The answer? Quite often. Many of the flagged regions could well be nothing more than statistical flukes, random fluctuations masquerading as meaningful signals. In the end, nothing in this initial search rose beyond what random chance could explain. Still, the fact that the search algorithm picked out the cold spot and a couple of other features meant that those areas deserved a closer look. If one of these was truly a collision imprint, it might have more than just a circular temperature anomaly. For instance, such a dramatic event could also leave subtle traces in the polarization of the CMB light, the way the microwaves are oriented as they vibrate. Polarization patterns can act like fingerprints at a crime scene, providing another layer of evidence about what happened in the early universe. Researchers examined the polarization data around these candidate spots, looking for the kind of swirls or radial patterns a collision might produce. So far, no definitive polarization signal has emerged that screams interuniversal collision. But the data continue to improve with new observations. By 2013, a new cosmic map by the European Space Agency's Planck satellite provided an even sharper view of the microwave background. With Planck's data, cosmologists repeated the hunt for collisions with greater sensitivity. If the WMAP search was like scanning the ocean's surface with binoculars, Planck was like surveying it with a high-powered telescope. Any disc-like bruises that WMAP might have missed, Planck aimed to catch. Planck's clearer view, however, found that none of the candidate collision signatures could be confirmed with high confidence. The cold spot remained the most noteworthy oddity, but even that could not be unambiguously tied to new physics. Essentially, Planck's results told us that if bubble collisions happened in our observable patch of the universe, their imprints must be exceedingly subtle or simply absent. While these searches did not provide a smoking gun for the multiverse, they offered something almost as valuable: limits and lessons. The absence of a clear collision disk in the CMB meant that such events, if they occurred at all in our past, were either too faint to detect or simply did not happen within the area of space we can see. In scientific terms, the teams were able to put an upper limit on how common or how large bubble collisions could be, consistent with our CMB's observed smoothness. That in itself is a remarkable piece of information. It's as if we peered into a vast forest and, finding no enormous scars on the trees, learned that if battles took place, they were few and far between. The search for cosmic collision signatures is far from over. New methods are being devised to probe the data in complementary ways. Some scientists are developing techniques to search for not just temperature disks, but other shapes or patterns that a collision might produce under different conditions. Perhaps elongated streaks or overlapping ring patterns from multiple encounters. Others suggest looking at the distribution of galaxies for any unusual concentric arrangements, though such signals would likely be even fainter and harder to untangle from the complexities of cosmic structure formation. Beyond electromagnetic radiation, there is also the tantalizing prospect of using gravitational waves, ripples in spacetime, as a probe. If two universes collided, they would have unleashed a burst of gravitational waves, tiny distortions in the fabric of space itself. Conceivably, some whisper of that ancient crash could still be washing through our universe today as a background of gravitational waves. Our current gravitational wave observatories are not sensitive to signals from so long ago and on such large scales, but future detectors might be. If we could one day hear an unexplained pattern in the gravitational wave background, it might be another clue pointing toward a cosmic collision. For now, the data we have speaks in a whisper, not a shout. The CMB maps contain no indisputable evidence of other universes bumping into ours. No clear bruises beyond the cold spot that demand an explanation outside standard cosmology. But this gentle outcome is itself a kind of answer. It tells us that if our universe has siblings, they have kept their distance, at least in recent cosmic history. Or perhaps collisions did happen, but our universe has healed surprisingly well. Its primordial scars faded into near imperceptibility. The cosmos, it seems, isn't giving up its deeper secrets easily. But the very act of looking has been transformative, pushing the boundaries of how we search for answers in realms once thought purely speculative. Scientists have gone from pondering theoretical multiverses to devising real experiments, however challenging, to find evidence of them. In doing so, they are expanding the toolkit of cosmology and our appreciation for just how subtle nature's messages can be. Our journey through these cosmic mysteries would not be complete without acknowledging a healthy dose of skepticism. Extraordinary claims, as we noted, demand extraordinary evidence. And so far, the evidence for other universes touching our own remains tantalizing, but far from conclusive. Many scientists look at the cold spot and other anomalies, and caution that we should not leap to exotic explanations too quickly. It is entirely possible, they argue, that these features are simply rare statistical flukes, or the result of some as yet undiscovered but ordinary cosmic process. In fact, calculations show that the cold spot, strange as it is, might still be just within the realm of chance in our standard cosmological model. Perhaps only 1 out of 100 universes like ours would naturally have such a large cold patch. Unlikely, but not impossible. That means we cannot yet rule out the idea that we just happen to live in one of those unusual cases, with no need for colliding universes or new physics at all. There are also alternative explanations, even within the framework of known physics, that could explain an oddity like the cold spot. Some researchers have proposed, for example, the presence of a cosmic texture, a relic defect in spacetime left over from the early universe, somewhat akin to a faint scar from a phase transition shortly after the Big Bang. Such a texture could, hypothetically, produce a large cold or hot region in the CMB without invoking another universe. So far, searches for evidence of cosmic textures have not yielded any definitive results either, but the point remains. Nature might have more than one way to paint a broad brushstroke on the cosmic microwave background. The multiverse hypothesis itself, while intriguing, sits at the fringes of what science can directly test. Some critics point out that if other universes are truly forever inaccessible, then their existence might be more a philosophical question than a scientific one. How can we confirm a reality we can never interact with? In this view, the idea of multiple universes, though born from mathematical theories, could lie outside the purview of empirical science, at least for now. To more skeptical minds, invoking a multiverse to explain a puzzling cold spot might feel like using a sledgehammer to crack a peanut. They would prefer to exhaust every conventional explanation first. And indeed, the burden of proof is high. A definitive discovery of a cosmic bruise from another universe would be revolutionary, which is exactly why it must be approached with caution and rigor. To them, the prudent course is to exhaust every conventional explanation before resorting to something as radical as a multiverse collision. Yet, alongside the caution, there is an undeniable sense of wonder that these ideas provoke. The mere possibility that our universe is just one of a multitude, and that we might have already glimpsed a sign of another, sends the imagination soaring. It transforms that pale, cold patch in the sky from a simple curiosity into a profound hint, a whisper that maybe, just maybe, the cosmos is far more expansive and varied than we ever thought. Even the skepticism itself is part of a grand scientific tradition. Challenging extraordinary ideas forces us to refine our thinking and improve our measurements. In a way, the multiverse debate exemplifies the very spirit of science, the tension between open-minded exploration and stringent verification. One cannot help but feel a sense of humility and awe at the implications of the multiverse concept. Time and again, humanity has discovered that the cosmos is much larger and more surprising than previously assumed. Once, we believed the Earth was the center of everything, until we learned it is just one planet orbiting an average star. Later, we realized our star is one of billions in one galaxy, which itself is one of countless galaxies in an ever-expanding universe. Now, the notion of a multiverse suggests that even our entire observable universe might be just a tiny bubble in an unfathomably vast ocean of reality. It would be the next step in our cosmic demotion. And yet, strangely, it is also uplifting. It means there could be endless new realms, new physics, and perhaps even new forms of life and consciousness beyond the horizon of what we can see. This blend of skepticism and wonder drives scientists onward. For those who doubt, the task is clear. Find more data, design better tests, and either detect evidence that elevates the multiverse from speculation to fact, or find mundane explanations that lay the question to rest. For those who dream, the possibility of a multiverse fuels creative thinking about what might lie beyond our cosmic horizon and how we might one day gather hints of it. Both mindsets ultimately push our understanding forward. The skeptics ensure we don't trick ourselves with wishful thinking, and the visionaries ensure we don't close our minds to astounding possibilities just because they seem outlandish at first. In the end, whether the cold spot is a message from a sister universe or just an odd quirk of our own, the discussion it sparks is valuable. It forces us to confront the limits of observation and the potential limits of our theories. It reminds us that there is so much we still don't know, and that the universe, or multiverse, is full of mysteries waiting to be explored. As we balance doubt with curiosity, we continue our cosmic voyage with cautious steps and open eyes, knowing that whatever the truth is, our pursuit of it will only deepen our appreciation for the majesty of the unseen cosmos. The observable universe, the portion of the cosmos we can see or detect, is enormous, but it is not the whole story. It is defined by the distance light has travelled since the beginning of cosmic expansion, approximately 13.8 billion years ago. Due to the continuous expansion of space, this distance extends even farther, reaching an estimated 93 billion light-years in diameter. The cosmic microwave background radiation, a remnant of the early universe, acts as a natural boundary beyond which electromagnetic signals have not yet reached Earth. Within that immense volume are hundreds of billions of galaxies, each with billions of stars. Yet, as vast as it is, this observable domain is only a finite patch of a much larger universe. Beyond that horizon, regions exist that are causally disconnected from what can be observed. They are effectively islands beyond the cosmic sea's horizon, forever out of sight. For all intents and purposes, those portions of the universe beyond our light horizon might as well be their own separate cosmos, unreachable and unseen. It's a strange concept to grasp, that there are places, even right now, that exist, but we can never observe, no matter how advanced our technology becomes or how long we wait. The speed of light is the cosmic speed limit, and space itself is expanding faster than light can bridge beyond a certain distance. In fact, distant galaxies near the edge of our observable universe are receding from us so fast, due to the expansion of space, that their light will never reach us. As time goes on, this horizon will not get closer. It will actually retreat. The accelerated expansion driven by dark energy means that, billions of years from now, distant galaxies that we can see today will slip beyond the horizon and fade from view. Future observers might find themselves in a seemingly emptier universe, with only the closest galactic neighbours visible, unaware of the rich cosmos that once lay beyond their reach. They will gaze into a much lonelier sky. The cosmic stage will gradually darken as those distant lights blink out, leaving only faint echoes of the past. In essence, the rich cosmic tapestry will have faded to just a few nearby threads in their sky. What lies beyond the observable horizon remains a profound mystery. One possibility is simply more of the same, an endless stretch of galaxies and structure, boundless in extent. If the universe is indeed infinite, then beyond our sight, it continues indefinitely, governed by the same physical laws. In such an infinite expanse, every possible arrangement of matter could exist somewhere, meaning that far, far away, there could be regions nearly identical to our own observable universe, and others wildly different. On the other hand, it's also conceivable that space, though vast, is ultimately finite, but unbounded. It may wrap around itself in a higher dimensional shape. If we could somehow journey far enough, far beyond what we can observe, we might end up back where we started, like circumnavigating a globe in higher dimensional space. Current observations suggest the universe is extremely close to geometrically flat, implying that it could extend forever. However, fundamental physics does not rule out a universe that is finite, but wraps around itself in a higher dimensional space. We simply do not know the full extent of reality beyond our horizon. And then there is the possibility of entirely separate realms, the multiverse hypothesis we have been exploring. In the case of the cosmological multiverse, our universe undergoes eternal inflation, leading to the formation of separate bubble universes with different properties. If our observable universe is just one bubble that underwent inflation, there could be other bubbles beyond our horizon with different physics and even distinct laws of nature. Those other bubble universes would be separated from us by regions of inflating space, still expanding too rapidly to traverse. They might have different fundamental constants, different particles, even different numbers of dimensions. They are truly other universes, and by definition we cannot see them or visit them. The only way they could ever affect us is if one bumped into our bubble, as we've speculated. But absent such an interaction, they remain forever out of reach. It is a humbling thought. Even if those other universes exist, we may never be able to prove they are there. They lie beyond an ultimate horizon, not just in space, but in principle. Still, humans are ingenious, and our curiosity about the unknown is unbounded. Although direct observation beyond the cosmic horizon is impossible, indirect methods may offer insights. We study ancient radiation, like the cosmic microwave background, to glean information about the early universe, which could hint at larger structures beyond observational limits. Similarly, we seek out the primordial gravitational waves from the infant universe, ripples that could carry information from moments even closer to the Big Bang, and perhaps provide indirect measurements of regions that cannot be seen using conventional telescopes. We search for subtle patterns or asymmetries in the distribution of galaxies and galaxy clusters, which might hint at influences from beyond our horizon. So far, these efforts have not detected anything definitive, but they help us constrain our theories and refine our understanding of the cosmos's global properties. And still, the quest goes on, refining our understanding of what the universe is, and perhaps isn't, beyond the edge of visibility. Contemplating the reality beyond our cosmic horizon can be at once daunting and inspiring. It underscores the limits of our knowledge, a reminder that no matter how much we learn, there may always be a veil we cannot lift. And yet, it also fuels the imagination. Maybe beyond our observable universe, there are marvels we cannot even conceive. Entire galaxies made of different forms of matter, or cosmic landscapes with laws of physics unlike our own. Or perhaps just endless stretches of silent darkness and light, continuing without end. The truth is, we don't know, and perhaps we never will know for certain. But the pursuit of such questions, the act of wondering and searching, enriches our experience of being part of this universe. Standing on the cosmic shore of what we can see, we peer out and ponder an ocean of the unseen. In that sense, we are much like ancient explorers, staring at the horizon of a vast ocean, uncertain if it marks the edge of all things, or just hides new lands beyond sight. Each breakthrough in our understanding has pushed that horizon farther, revealing that the cosmic ocean is far larger than we imagined. There may be no final edge, just more to discover. Beyond the observable horizon stretches the ultimate unknown, a reminder that the universe, and whatever lies beyond it, is richer and more surprising than we can possibly envision. And though we may never grasp it all, we will keep striving to push against that boundary, driven by the same spirit of curiosity that has carried us from the caves to the stars, and perhaps, one day, beyond. No matter what, our desire to understand will keep propelling us forward into the unknown. For as long as there are horizons, we will yearn to cross them.